get started, and I think everyone's here. We'll start now. Hi, thanks everyone for coming. Hopefully Mark will be here later to give you his wonderful talk. He's around town anyway, I just haven't heard from him this afternoon. He gave a talk, he gave the same talk in Trinity today, so we should be about. My name is Daniel, I'm one of the members here of the Hackerspace, and we like to do events that draw people in. We like to do stuff for Space Week and Science Week and Engineers Week, and any other week we can give free advertising and drag people in and advertise the space. So I'm not sure how long the space has been going for. It's about 8 years, Gary.
Yeah, coming up 8 this January.
So we started in a tiny place, we moved to a medium-sized place, and now this place is probably too big. The bigger the space, the more room for the junk. So we don't get any government grants, we're just self-funded. It was one of the ideas behind setting up the space. We're not reliant on the next funding round and all that sort of messing. We can give you a tour afterwards. Most events run here are free, so you can see them on the website. There's a mailing list and Twitter accounts and all that sort of stuff. If you want your own key, which every member has their own key, it's usually €45 a month. That gives you 24 hours a day, 7 days a week, access to the place. If you want to come here, there's specialised nights, like every second Monday is electronics. There's a craft night now on, I think it's every second Wednesday. There's lockpicking, if you're interested in that. What else have we got? Anyway, there's a CAD night, so if you want to do 3D printing or laser cutting. There's a CNC now. There's a CAD night as well. So you can see all that on the website. So first up we have Connor. Connor's working with little small satellites, and he's going to give a talk. And then I'll give a talk on the projects I've been working on with the space station. And then hopefully Mark will be here and he can give the talk on his work with NASA. So maybe a round of applause here for
I cannot see anyone. Talking to the darkness. My name is Connor. Basically, I graduated from DCU doing electronic engineering about 4 years ago, and since then I've been working on sensors and satellites and that kind of jazz for about 4 years now. Started off working with satellites out in San Francisco for a company called Spire, who started off doing CubeSats for schools and education, and basically selling time on the satellite to do so the students could do their own experiments, such as like measure the Earth's magnetic field, and just basically democratize space education. But they slowly moved towards more commercial applications, so get into that. But I guess we'll start with the history of it all. Space, as you all know, kind of the first pushes to space were American government funded. They got us to the moon, but after that they kind of trailed off a little bit. The shuttles going to the space station, it went for a good probably 30 years, up to Mir at first, and Skylab, and currently the ISS, but kind of floundered a little bit. Got from Earth to the moon in about 9 years, and that was in the 60s, and we haven't gone back since. So when this guy was running the show over there, he kind of made a grand proclamation to say that we're going to go back to the moon, and that was under the Constellation program, and they started working on that for a while, and then this guy got in charge, and they scrapped it. Instead, well, we've been to the moon, but let's go to Mars, where we can actually colonize it and start looking for life, and actually not just flounder and do what we did with the moon, where we went, we're going to go to the moon, that's it. Right, come back home. Nothing there for us. And that went ground for a while. We're pushing that now. Elon Musk is planning on going to Mars sometime in the next 10 years, in theory. And then this guy got elected. And now his grand plan is we're going to go further out. We're going to go to Europa, as announced about 2 days ago. So we're noticing a pattern here. Government funded space is kind of dependent on the politics of it all and what the guy in charge kind of wants to do. Now, we've done some pretty neat things in the meantime, but they have cost many billions. I'm not sure on the exact figure off the top of my head, but the space station is in about 20 billions, and the Ariane 5 there on the right, which is the European rocket that they're working on at the moment, is going to be about 6 billion. Anyone got that in the pocket? Don't think so. So, you know, the space station has its uses. I'm not going to deny that at all. I've launched, well, not me personally, but the team that I work for has launched CubeSats from the space station. Basically, that right there in the middle is a box with a spring in it. And they open the box and the spring pushes out the satellite and it goes off in space, and you now have a satellite independent on its own. It's really box simple, it really is. How many people here have heard of CubeSats before? No? Okay, so about half is anyway. But yeah, they're a lot cheaper than your standard satellites that are the size of a truck and cost about $1.5 billion to develop. They're pretty small. They're about 10 centimeters by 10 centimeters, and this one is a 2U, so it's by 20 centimeters on its longest point. So they're a lot smaller, a lot cheaper to launch, and cost about maybe 100,000 to launch one, which is a lot more in the realm of a group of people with maybe a small bit of funding and an idea to go behind it. What I was working on before was one of these, which was called an Archisat. So it was basically a satellite that had an Arduino running in it, and that basically you could program in your Arduino IDE and write your script and upload it to the satellite through our radio. And you could there'd be a bunch of sensors, as you can see on top, such as infrared, magnetometer, acceleration, cameras. There was a camera in there as well, so you could basically do what if you had a satellite up there. Well, yeah, for about maybe $200 US, you can buy about an hour's worth of flight time. So you can toy around with that and not need to actually have to deal with all this. This is like software service. Now the end result is a little more complex than this, but you can buy one of these as a kit. Now I'm sure a lot of you actually have Arduinos, so you probably don't need the kit. But if this is basically for schools, so that they could actually see for themselves firsthand what kind of size they were dealing with. So this is how it's been improving lately, and basically companies are starting to realise just how cost efficient it is to actually get data down using these small CubeSats, and they send them in bulk, sometimes in groups of 60, and basically instead of sending one big satellite, you can send up a small one, a lot of small ones rather. How you get them up there are these. Unlike the predecessors, which were government funded, these are a lot cheaper and a lot more efficient, because we actually get to reuse them by landing them on a barge, like here. So basically, you can send a rocket up, and as you normally do, first stage, second stage, and separation, where the satellite can go off on its own. But unlike what we've been doing up until now, the rocket can use some of its remaining fuel and basically use that as a slowdown mechanism to come back down to Earth in somewhere that is a little out of the way of things that don't like exploding things around them. But this is significant. This is going somewhere, to say the least. This is a render of the proposed rocket that is going to go to Mars in the 2020s. And that's a Saturn V rocket, which is the biggest rocket we've made so far. And stats are pretty impressive for something that's a lot cheaper. But this is all great and all, but why? What's the actual end use? Well, this is a picture of basically the ships around the world. And after we did the whole education thing, when I was working over in San Francisco, we started tracking ships, because once you're about 100 kilometers away from shore, ground-based systems can't really see over the horizon. So you need something else to do it, and there's something else to satellites. But something like 80% of world trade goes through ships, especially in an area around here where all the Somali pirates are. So if you can't see them when you're out in the ocean, if you can't see your ships when you're out in the ocean, it's kind of hard to tell if you've been raided and where you should send a rescue team and all that. Another useful thing is, for example, China. If they're saying their GDP is like growing 50% a year, and you know where their ships are going and what's on those ships, you can start calculating yourself what are they actually exporting and what's the value of that. And it's a nice little bit of truth. Then the current company I'm working for, we're building satellites for tracking airplanes. So I don't know if you remember the Malaysia Airlines plane that went down in the middle of the Pacific Ocean. But the reason it went missing was there was only one satellite overhead at the time, and they knew how far away the plane was when the plane went down, but not exactly where along that line it actually was. But if you had a lot more satellites up there, you could start narrowing it down by having another arc of another data point of triangulation. But when one of these satellites costs multiple billions, they tend to only have a few up there. So we're building smaller satellites, smaller CubeSats, that can bridge that gap while not actually increasing the cost. Other applications would be agriculture, so you can take pictures in space, figure out what's growing, and how are different fertilization rates affecting the local area. And that's great information for farmers, needing to know where they need to put down more fertilizer. It saves a lot of money. And then there's these guys. There's a company called Made in Space, who are 3D printing on the space station itself, so that instead of needing to send up rockets every few months to resupply the astronauts, you can just start printing off equipment as you need it, as stuff breaks, which is a bit more important when it comes to resource utilization. But and then there's this, which is this asteroid is called Ryugu. There's a mission planned from the European Space Agency to go to it, but if we're to go to space and actually live there, we're going to need materials to build stuff, keep it alive. This satellite is about 1 kilometer in radius. It's worth 95 billion in raw minerals, such as lithium, platinum, palladium, rare earth metals, and that's not a big one. That's a medium-sized one. It's got a special. It's got all the really rare stuff in it. many years ago, the Lincoln Memorial over in the US was capped with aluminium because it was more expensive than gold. That was before we figured out how to extract it from the ground. It was really rare. Back then, fine cutlery was made from aluminium, not silver. But now, there's a bunch of Coke cans in the corner made of it. If we can actually get a source of platinum, there's a lot of uses for like catalysts, like in our cars, that kind of stuff. So we can open up a good few new doors if we go for this stuff. But there's a historical precedent for this as well. Gold rush, back in California in the 1850s, where basically we had already Spain had already financed Columbus and all that to find a new world, and that's what we're doing with rockets and the space station at the moment. But eventually people started realizing there was actual money to be made out there, and they went on their own free will to find their own riches. And at first it was just about the minerals, but over time, because there was a lot of people out there, people need services to get on with their lives. People need a haircut. But a lot of these buildings were built just from the scrap of ships that were coming ashore, because a lot of these ships, the people that were manning these ships and sailing them to deliver the passengers also heard about the gold rush and just abandoned posts and went to become miners. So there was no one left to sail these ships back to where they came from. So the founding of San Francisco here in the picture is the wood from the ships were used to rebuild the city around them, and now it's what, 6th largest GDP in the world if California was a country. But where there's going to be people down the line, we're also going to need, well, stuff. Not everyone's an astronaut at the end of the day. So that's where this. Remember Hal from Space Odyssey? He was initially designed to be a piece of software to help out the astronauts, and he went skewy and all that. But that's why we need good design and good engineering done on the ground first, so that those kind of problems that you see in movies don't happen. But on the right there is a picture of a whiskey glass designed to work in zero gravity, because liquids don't tend to stick to the ground. So basically it has a coil that the whiskey sticks to, and has basically a lid here. It's basically a sippy cup, but it's a fancy sippy cup. When people are making like these kind of niche things, it's like when you send up regular people, unlike astronauts, you can't be drinking from what is essentially like Capri Sun packs for the whole time. So good design is going to be needed for actually being able to live up there. And there's a lot of opportunity at hand for the commercialization of all this. But pretty much right. Questions?
Any questions here, just to remind?
Can you come again? How expensive is to get a cube on an orbit?
Say that again?
How expensive is to get to the small 10 centimeter by 10 centimeter by 10 centimeter cube on an orbit?
About €100,000. Currently I'm working on a satellite that is 5 centimeters by 5 centimeters by 10 centimeters, and that costs about 20,000. But for tracking, it's like tracking airplanes, for example, is 45 million a year endeavor. So on that it's valuable, and there's a trade-off. You ask me?
Do these cubes have their own propulsion in them at all?
Uh,
So how about space shuttle?
Okay, two questions. In Earth, we have magnetic field to work with, so we don't need actual propulsion. We just need to throw up some electromagnets, and we can start orientating ourselves that way. but there's a project going to be launched pretty soon called CAT, and basically uses water as a propellant because it'll expand massively in a vacuum. Now, it's not enough to run a rocket, but for pushing a small cube, it's pretty fine. In regards to space debris, God, I hate this question, because everyone has seen Gravity and thinks that is a massive problem.
I actually haven't.
Great film.
But basically, the space between the Earth's, if you have a globe of planet Earth, like just a model one, the varnish on the surface of it is the size of our atmosphere to scale. And that's about 100 kilometers. Geosynchronous satellites are about 22,000 kilometers up. So when a satellite breaks up in low Earth orbit, it's not going to get up to the geosynchronous satellites. Also, the problem is when one of these big satellites explode, they create lots of smaller pieces that break and crash into other satellites and creates a Kessler syndrome, and that just propagates. But when it comes to smaller satellites, if you break one, it's not going to create a lot of debris. I think it's the odds of hitting a CubeSat, a 10 centimeter by 10 centimeter CubeSat, is 3 trillion to 1 with a T. I can think of a few other things I'd rather gamble on, yeah, compared to the actual larger satellites that are up there at the moment, these CubeSats, they generally re-enter into the Earth's atmosphere between 6 months and 4 years. So unlike the larger ones where there are still satellites up there from the 60s in the graveyard orbits, they generally provide a much smaller problem than what we already do anyway.
How do you think cube rupture is going to go? How soon do you think cube rupture will be complete now?
We got one from start of the design stage to space in 4 months. The main problems was mostly the paperwork and actual just waiting for the rocket to launch. Because we had a lot of the submodules, like the power system, the computer can be bought straight off the shelf from hardware providers, and it's basically like assembling a PC, and it's just a matter of putting the software in that you want to do the applications. If you really get your work together, the main problem is just getting the launch contract in place rather than actually the engineering of it. Because if it's only about software, you can update software in flight, so you can be constantly iterating and improving the satellite as the mission goes on.
Okay, thanks very much, Connor. I'm doing the next section here. I deliberately tried to not make it too technical. Loads of videos and nice sound, so we'll see. Does the laptop work for starters? Well, there's Windows sounds anyway. So this is a talk I've given a couple of times. I gave it over in London and I've given it in Dublin before. And it's about a project I've been doing for about the last 3 or 4 years. It's about amateur radio satellites, is the description of the talk, and receiving live video from the orbiting space station. So there's the TOG logo. I'm also a member of South Dublin Radio Club, and that's our logo there on the right. And the last time I gave the talk was with this astronomy group. So I'll start off with a video. So this video was taken from the space station. It's been quite edited, and it shows the view from the space station at night time. So this is sped up a bit quicker than the space station really moves, but you can see the storms there. You can see the street lights. I can't recognise which country this is, but sometimes you can pick out specific countries at night time. You can see the solar panels are adjusting there to line up to catch the sun. As the space station's always moving, it has to adjust the solar panels to catch the sun. You see the sun rising just there. Okay, so that's just an introduction to the space station. And there's my contact details if you want to know more about the project. I'll say I'm a member of the South Dublin Radio Club, a member of TOG as well, and my other slides were changed to Science Week, but that's Space Week. So I'll explain a little bit about orbits. So we were talking earlier about launching satellites. So most of the smaller satellites are in low Earth orbit. So it's that purple line, and they travel around the world and they're moving constantly. And you can see as the space station there is moving constantly. And that'll affect what I'm doing later on, which is trying to receive signals from it. There's a thing there called polar orbit. So the polar orbit is interesting in the fact that it goes over the North Pole each time, and it goes over the South Pole each time. And one of the benefits of doing that is the Earth is rotating all the time. And because the Earth is rotating all the time, but it's rotating around the North and South Pole. So if you go over the North and South Pole, what you'll do is you'll go from north to south on a map over and over and over again. And if you do the position right, you'll actually pass over every point on Earth. So for example, if you want a spy satellite to film every part of the Earth, you might put it in a polar orbit, but also you'll want it in a polar orbit, but you'll also want daylight over where you're doing it. So what they call it a sun synchronous polar orbit. So you'll put your satellite maybe over the North and South Pole, you'll put a spy camera on it, and you'll make sure it goes over the same point at midday every day. And it'll be midday at that point in the world every time you go over that point. And so, for example, you might get a new photo at midday of every day of Dublin, and at midday in London, and midday in France, and midday in Germany. And then the more interesting, simple thing is to look at what's changed. Is there any new buildings? Is there anything changed? And if you take it at midday every day, you know you've probably got good sun. So some of the spy satellites will be in polar orbit. Also, a lot of the smaller weather satellites will be in polar orbit. Because say, for example, if you wanted to pass over Europe every day, well, if you put it in a polar orbit, you can design it so it passes over Europe all the time, and if for a European weather forecast. So there's a high elliptical orbit, which I'll kind of skip, and then there's geostationary orbit. So geostationary orbit is you're way out, and you're flying around, and you're doing one orbit per day, and you're flying around the equator. And from the Earth is spinning, but from the point of view of the satellite's moving, but from the point of view of a person on the ground, the satellite looks like it's not moving at all. So the problem I have is I'm trying to pick up something that's low Earth orbit, so I need to keep moving where I point. But if it's in geostationary orbit, you never need to move to point at it. And the great thing about that is if you're on the ground, you're trying to get a signal from a geostationary satellite, you point your antenna at the satellite and you never need to adjust it again. And the most common one people would use is Sky TV. So Sky TV has to be in geostationary orbit. Otherwise you have to go out and keep adjusting your Sky dish as the satellite kept moving around the place the whole time. So Sky is in geostationary orbit, and most TV satellites that we use are in geostationary orbit. But one of the problems is they're very, very far away. So at the start the signal from Sky was actually quite weak. So anyway, I'll go on with my next little bit. The space station, as I was saying, it's not constantly above the same location. It keeps moving. So one website you can use to see where the space station is now, and more importantly, see when it's going to pass over Dublin or over Ireland, is Heavens Above. It's quite easy to do. You put in where you are, and it'll tell you when the space station is going to pass. One of the interesting things about Heavens Above, it'll tell you when it's dark where you are, and it's sunlight where the space station is, which is normally about an hour after darkness here. You might be able to see the space station with the naked eye. So if you look at Heavens Above, sometimes you can see when the space station is going to be visible. And if it happens to be a clear night, and I think it's a clear night tonight because it's so cold, you'll actually be able to see the space station for a couple of minutes, usually pass over from the west to the east, usually kind of south of Dublin. Normally the highest north it goes is Cork, but you can see it from Dublin passing over Cork. So I'll move on to my video 2 if I can find the right place. No, that's not it. See, this slide, heavily prepared. Oh, which one is it? Oh, there we go. So this gives an example of the orbit of the space station sped up. And I'll see, does it work? So I'm trying to pick up a picture of a signal from the space station. So the space station is the red dot. The amount of the ground you can see is the white circle, and the red line is just its general orbit. So you can see there in America, sometimes it's passing over America quite good, other times it's not. Sometimes it's passing over Australia, but the next time around it mightn't pass over Australia. So what we're looking to try to do is get a picture in Ireland. So you can see sometimes it doesn't pass over Ireland, and sometimes it does. So again, I use the website Heavens Above or other sites to predict when it's going to pass over Ireland, so I can get TV pictures from the space station. So I'll go back to my slideshow. So this is an exaggerated image of the satellites around the world. So they're much bigger than they are in reality, but there's loads of little satellites doing different things. Now some of them might be space junk, some of them are working satellites, some of them are secret, some of them are different countries. But there's loads of little satellites for doing different things. A lot of them are in different orbits, they don't crash into each other. There's so much space up there anyway, it's quite unlikely they'll crash into each other. And most of the satellites in low Earth orbit will come back to Earth within about 20 years. So even if they're up there and they're broke, in about 20 years they'll crash into the sea somewhere. So I'll skip over this a little bit, but we use radio frequencies. So the radio frequencies we're using for sending the TV pictures are up near where the satellite signals are broadcasting. So if there's something in the way, you won't get the signal. And the main problem we have is that the Earth is in the way. So these are some examples of amateur satellites. We were talking earlier about CubeSats. So the one at the top left, some of you might recognize it as Sputnik. And Sputnik wasn't really an amateur satellite, it was built by the Russians. But they actually broadcast on an amateur frequency, which meant anyone with the right radio could hear them. And it deliberately announced what it was broadcasting. And the reason they did that was to prove they were the first one in the world to put a satellite into space. So that satellite, while it wasn't an amateur satellite, was actually broadcasting on amateur frequencies with the intention that amateurs would pick it up. Then the bottom right is a larger type amateur satellite. You can see there's solar panels on some of it. And then often they have cameras and antennas and different things for different projects. So some satellites look down at the Earth, and then some satellites look back at space as well, looking at planets and things like that, or maybe looking at the sun. So my main talk is about the space station. So what is the space station? A lot of people don't know. It's not just NASA, it's the Russians, it's the Japanese, it's the Canadians, and the European Space Agency. So it travels about 7 kilometers a second. It goes about 27,600 kilometers an hour. It's not that high up. We were talking earlier on about the orbits of CubeSats. It's only 400 kilometers above the ground, which means it's only about 200 or 300 miles up. And that's why you can see it quite easily when it goes over Cork. It was launched in November 1998. It may end in 2025, depending on budgets and what lunatic's in charge. And it cost $150 billion US. So if anyone can give me a few quid towards my work. So I'll explain to you why I wanted to pick up video from the space station. One of my hobbies is picking up video, but I found that the space station was going to start broadcasting video. If I can hit the right button.
Hi everyone, I'm Tim P and welcome aboard the International Space Station, where we're orbiting Earth 16 times every day. One of the most rewarding activities that some astronauts undertake on orbit is to talk to schools using the space station's ham radio. Now these are events that are planned by ARIS, which is a worldwide group of amateur radio volunteers who are dedicated to introducing young people and students to science, technology, engineering and mathematics. Now this is the equipment here in the Columbus laboratory, which consists of a handheld radio, a headset, and we also have a ham video unit. Now as the International Space Station orbits above your location, a radio link is established between the ISS and your school. Now because we're travelling at nearly 18,000 miles per hour, which is an incredible 25 times the speed of sound, we usually get about 9 or 10 minutes of good radio contact before losing the signal. So about 5 minutes before the scheduled start time of the contact, I come into the Columbus laboratory and configure the radio so that I'm on the correct channel. And sometimes I'll set up a ham video too. Just before the predicted time, I'll begin to start calling the school, using the standard amateur radio calling techniques. For example, if the call sign of your school was GB4 Fun, I would say Golf Bravo 4, Foxtrot Uniform November. This is Golf Bravo 1 Sierra Sierra, listening and standing by. Now at your school, the radio operator will be listening for my call, but may also transmit and try to call me as well. You'll probably have a much more powerful transmitter on the ground than we have up here on board, so I'm likely to hear you before you hear me. Then, once we can hear each other, then comes the best bit, which is actually talking to the students and answering the questions. Once I've answered all the questions, we use the remaining time to say goodbye to each other and end the connection. I'll then spend a few minutes configuring the radio back into a rebroadcast mode, and then I'll go back to my day job, which is of course doing science on board the International Space Station. ARIS is a brilliant opportunity for astronauts to talk to school pupils. It's really rewarding to hear how excited the students are when they're talking to somebody up here in space. And it's a true privilege to be able to inspire our next generation of scientists and engineers through amateur radio.
So anyway, that video just explains what a school contact is. But I didn't even know much about that when I heard they were going to start broadcasting video. What I heard is they were going to put this box on the space station. So you see there's a power switch, a video camera switch, and there's a connection in the bottom right just for an aerial for outside. So I just wanted myself to try pick this up. So being mean, I couldn't afford all the fancy equipment to pick it up. So I went cheap and nasty. I got a satellite dish that was sitting in the shed for years and was a bit bent. And you can see the high-tech setup I have here. So you can see the bent corners of the satellite dish. There's the grey bit in the middle is actually a bit of water pipe, and there's a kind of a spring-shaped thing inside. And I needed to point this at the space station. The problem is it was a cloudy day, and you can't see the space station. So you can see the yellow thing I have there is the spirit level. So when the bubble is level, you know it's horizontal. And that one actually has a little digital display, so you can tell which way to point it. I also had a sheet of paper on the ground with north, south, east and west. And I had a bit of a guess. I had a cable going from that into the car, and in the car I had a receiver for receiving the video, and then I hooked it into the audio of my car, and I went boop, 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 when the signal got stronger, and that was what I was doing. So this was the first time they ever broadcast video, and we got some video. So after I sent the video to the guys who were doing it, they said, oh, you're the first person outside of the main group to do it. We're actually looking to have stations around Europe. Could you, if we give you the equipment, set up a station in Ireland to receive the video? So I said, oh yeah, no bother, till I started investigating what I needed. So you need a good location where you can see the horizon. The further south the better, because the space station doesn't come over Dublin, it goes over Cork. And so anyway, I talked to some people at the National Space Centre then in Cork. The European Space Agency paid for some of the equipment, and myself and Tom, and with the help of Dermot, who's here tonight, we brought all the equipment down in the trailer, threw it up on top of the gatehouse. That's the security hut there. There's a little motor on the bottom that turns the dish one way, and there's a motor up the top that turns the dish up and down. We have special software inside that tracks, it asks NASA when is the space station due, and it turns and tracks the signal. So that sounds great, getting a signal from space, but what do you actually get? So this is an example of what we get. So you have all these settings, which basically you set them to what you're told to set them to. You hope the lights at the bottom go from red to green, which they have in that picture anyway. If they don't go green, it means your dish is probably pointed the wrong way, which does happen at times. And you get video like this. So what we do in Cork is we receive the video from the space station, and then we send it directly to wherever the school is. Now the school may have a video system at the school, or they may not. But there's a station in Ireland, in France, in Italy, a couple in Italy, and in Poland at the moment. And what we do is, as the space station is coming over Ireland, oh, there's one in Portugal as well. Either Ireland or Portugal will get it first. We'll send the video to the school, and then France will probably get it next. Then Italy will get it next, and maybe Poland will get it last. So between 3 or 4 or 5 stations, we can get maybe 10 to 20 minutes of video. So the idea is when the school kids are talking to the astronaut, not only can they talk to the astronaut, They can also see the astronaut. And this was never available up until a year or two ago for these school contacts. So this gives you an idea. These are the different stations around Europe, and you see some of them have a picture, some of them don't have a picture. Some of them have a picture, but it's frozen because the space station has gone past them. So usually the picture just freezes when you've lost the signal. So I'll show you this last video, which gives you an idea of a school contact. Now it's actually been quite edited.
What's up? This is John Breyer, HTJ.
Hang on, I'll just pause this. So it's actually been quite edited. What we did is we added in the school's video, and we added in the different videos synced together. Because normally what I record is just what the astronaut sees. You don't see any school children. So we wanted to combine it to a more interesting video. So I think 1 minute 20 in is where the good bit starts. So that's clear enough. So this is the school calling the space station. At the start they get audio, then later on they get audio and video.
Are you ready for your first question? Over.
Hi, this is Matt. What do you need to know? So are you back in space? Over. Hi, this is Austin. Are there any friends going to the George, please knock on the front door. As you go around over. Tim, it's David M0X3. We have you on TV. Give us a word. Here's your next question.
Hi, this is Sophie. What experiment would you like to add to your mission based on the experiences you have had? Over.
Hi Sophie, I would like to see us doing more of the medical research, investigating some more vaccines and looking into new drug methods as well. I think that's some of the most exciting research we're doing up here. Over.
Hi, this is Max. In what ways does the lack of natural sunlight and fresh air affect you on the ISS? Over.
Hi Max, I love opening the windows in the cupola when I'm in Node 3 or in the Japanese module. I love the sunshine coming through the windows, and it does make a difference. It does kind of brighten up your day and make you feel better. And you just get used to the fact that we see so many day and night cycles. Over.
Hi, this is Charlotte. How do you get changed in space? Won't your clothes go everywhere? Over.
Hi Charlotte, they do go everywhere. We have to use bungees. We bungee our clothes down so they don't float off and you don't lose them. Over.
Hi, this is Eden. One of the experiments you are conducting in space is to measure fluid shifts in the body. In what way does this help us back on Earth? Over.
Hi Eden, that's a great question. Fluid shift really kicks off the whole process of the changes to our body. It's because of the fluid shift we get greater pressure in our head and we start to lose bone density as well. So that triggers all the changes, and it's by changing things in our body that we can learn about our body and we can investigate these things. Over.
Hi, this is Thomas. With the basic design of current spacecraft dating back decades, where do you think the next leap forward in spacecraft technology will occur? Over.
Hi Thomas, yes, I mean we're playing with basic rules of physics and gravity here and laws of motion, so I think that we're going to see big changes to our spacecraft in terms of our transit to Mars and transit to Moon. But in terms of getting to low Earth orbit, I don't think we're going to see many big changes that we have in current spacecraft design. Over.
Hi, this is Emily. How different was the training compared to the experience of actually launching into space? Over.
Hi Emily, the training was so good that it really prepared us for launching into space, and there are very few differences between what we were training for on ground and how we live and work up here in space. Over.
Hi, this is Millie. With improving technology on Earth, are there experiments that you are currently carrying out in space that could one day be repeated on Earth? Over.
Yes, there are loads of experiments up here that we're doing that could be repeated on Earth. I think that it's going to be a long time before we manage to sort of counter gravity for a long period of time on Earth. So we use parabolic flights and drop towers. But the benefit of being up here in low Earth orbit is, of course, we have microgravity continuously, so we can do those experiments for a very long time. But we do repeat the experiments back on Earth, of course, to see the changes, to see what's difference between space and Earth. Over.
Hi, this is Erin. Which materials being developed with the electromagnetic levitator will have the largest impact on the development of greener living? Over.
Hi, Erin. Well, I think the metal alloys are the one area of research that are going to have the big impact on greener living, because that will affect how our engines are designed, and in particular our commercial aircraft turbine blades and turbine engines, for example, which will cut down fuel production and cut down fuel usage and have a good impact in aviation. Over.
Hi, this is Maddie asking Noah's question. Since being in space, what has been your most amusing dream? Over.
Hi Maddie, do you know, I haven't dreamt much up here in space, and when I do, I dream of Earth. I haven't yet dreamt of being in space, and I think it's because we sleep quite heavily up here actually. I sleep quite well here in space. Over.
Hi, this is Austin asking Livy's question. If everyone in Britain turned their lights on and off at the same time, would you see it from space? Over.
Hi Austin, yes, you definitely would see it. You know, we would see a small village if you turned your lights on and off. It's amazing that the lights really stand out very well from space. And certainly a major city turning their lights on and off would stand out very clearly. Over.
Hi, this is Sophie asking Ella's question. Which part of the Earth do you like orbiting over the most and why? Over.
Hi Sophie, I love orbiting over Africa. It just looks beautiful from space. It's like flying over a canvas of art. And also northern Canada is beautiful, especially right now with all the ice and even the sea is frozen up there. Over.
Hi, this is Max asking Amy's question. With sunrise and sunset occurring 16 times a day on board the ISS, does it have any noticeable effect on your body clock? Over.
Hi Max, that's a great question. Yes, it does. You know, if I'm looking in the cupola late at night when it's bright sunshine, it does take me a while to get to sleep. So I try not to do that. You have to kind of try and trick your body that it's nighttime when it's time to go to sleep. Over.
Hi, this is Charlotte asking Mimi's question. How does being in space make you relate to your place in the universe? Over.
Hi Charlotte, that's a great question. You know, I mean, being up in space gives a different perspective and it makes you realise how vast the solar system is, how vast the universe is, and also it makes you realise that our planet, you know, it has no borders. It's got massive weather systems that affect all continents, and so it does give you that perspective of the planet as a whole. Over.
Hi, this is Eden asking Bruno's question. Is there a song or a piece of art that you think reproduces the feeling of being in zero gravity? If so, which one? Over.
Hi Eden, well, there's nothing particular comes to mind, but you know some of those pictures where things look different upside down. For example, it might be a beautiful woman one way up and an old haggard woman the other way up. I think that's great because it makes you realise in space, of course, we have a different perspective depending on which way up we are. Over.
The GB2CNS returning. That was fantastic, thank you. Everyone here would like to say a big thank you.
So that gives you an idea of a school contact. So I helped out with some of the UK school contacts. I'll see if I can find the video. So I helped out with some of the UK school contacts, and I'm looking to try organise some in Ireland. So we're hoping to have one with Dublin school children and Cork school children maybe later in the year. And we don't know if we'll get video with it. The video system is very new and it's not always used, and it's quite difficult to organise, but we're hoping to at least have voice, and we're hoping to at least have a few silly questions as well. So we've applied, but there's going to be French astronauts on board the space station for the next few months, so they're trying to give priority for the French astronauts to talk to French students in French. So that's what's going on at the moment. So that's the kind of projects I've been working with. If you have any technical questions, I can answer them afterwards. As I was saying, after the main talk, we'll give a tour of the space. We'll explain a bit about the space, how we're non-for-profit and we don't get any grants, and we just pay for the place ourselves. Most events we do here are all free and open. And as I was saying, after Mark finishes his talk, we'll give a quick tour. So I'll put on the light for a minute, so it doesn't fall on his face. Is he there? Is he here? Who wants? Is he there? Is he outside? We're waiting for you here. You've got 2 hours anyway, so you don't need to rush you too much. This is your second time today giving this talk now, you must be worn out.
All good.
Is there a bathroom in here though?
Yeah, so just through there and kind of round to the right. He's obviously got stage fright.
Does he have his big bathtub outside? He jump into him. He gets homesick.
Connor, do you want to try to slide on this USB stick on this machine? I think mine's just gone to sleep. Alright, mine's back up again. Whatever. I was thinking about it. Here, you can up the faster there. Because I know he was using a pointer last time we gave a talk. So. So yeah, you can work away with the chocolates and stuff there. Just a little, yeah. Which one is it? I don't know. Take copy it across to your computer. Yeah.
Oh, I don't think I should some of these.
Maybe not.
Presentations.
Oh, well, we'll let them decide. I'd say it's Irish experience, but there's a few. No, say it's Irish.
No, it says one of these two probably.
Oh, well, we'll leave it a minute. Oh, well, here, will you hook this in as well? Go in here, is it? Yeah. You pick which presentation there's a few. It should work then. Oh, sorry, there's a mouse there, maybe that's hooked in. That'll make more sense, would it? Is it working?
I saw something up here, it seems to be jumping. Oh, there we go. Okay, very sensitive.
No.
Yeah, it seems to be working now. I'll knock off the lights. If you want to grab your drinks there and sit down.
It's like a yellow. I'm not sure just to bloody hear it.
Yeah, just. You can get the change. So I'll just say thanks to Mark for coming, and you may as well get going. He can explain better than I can explain what he does for a day job.
So thanks very much for having me, guys. This presentation, don't want to walk too much in front of the projector, is about NEMO. NEMO is NASA's high fidelity training analog for the astronauts. NEMO stands for NASA's Extreme Environment Mission Operations. One of their best acronyms as far as I was concerned, except they didn't come up with it. So NEMO was actually taken from Captain Nemo, 20,000 Leagues Under the Sea, from Jules Verne. And this entire concept was to design and develop a training environment for astronauts that wasn't just a bubble or a habitat or a tent out in the middle of the desert or up in the Arctic Circle. One of the things that we found over the years is that these type of environments, oftentimes the astronauts would go, they'd work for the day, and they'd go to a hotel, they'd go to the tent, or you'd open the front door, get out, and it almost destroyed the fidelity or the quality of the simulation. Years ago, the guy that came up with this concept was the chief trainer for the Space Shuttle simulator. So he had put several missions, probably up to about halfway through the Space Shuttle program, if not more, all of these through the Space Shuttle simulator. And he ran every case of worst case scenario that you could think of, trying to train these crews. And one of the things that he found is no matter how bad it got in the simulator, at the end of the day, the astronauts went home. And he just felt that the level of fidelity and the level of training that these crews underwent, there was something missing. So we went and found Aquarius. Aquarius is the world's only underwater research laboratory. It's based down off the Florida Keys, about 5 miles off the coast, on the bottom of the Atlantic Ocean, about 20 meters down, owned by Florida International University. At the moment, it's the world's only underwater research laboratory. There are or have been other smaller habitats, but at the moment, this is the world's only fully functioning laboratory. And the entire concept was that taking astronauts, putting them down into this habitat for 1 to 2 weeks at a time meant that at the end of the day, they were still in mission. There was nothing simulated about this. This was a real-world mission that had a high up-tempo that was designed to push the crews and deliver the best training environment possible before they went into space. So he went and contacted the chief medical officer for NASA at the time and tried to bring him down, and eventually, kind of after a lot of persistence, agreed to come down. And his basic attitude was, we train astronauts, we send them into space. Why in the name of God are we bringing them down and putting them underwater? But anyways, eventually he agreed to go down, and he went with Bill and went to visit the Aquarius habitat. He went down, and the only way to get down to the habitat is you bring them both out from the shore and you dive down and scuba. And then you can go get into the wet porch. It's actually through a moon pool, and you take off the scuba gear, climb up the steps, and then into a dry environment. He was down there about 5-10 minutes, and he was visibly irritated. And eventually, after about 5-10 minutes, said, okay, I've got it, let's go. So they went, put their gear back on, dove back out, back onto the boat, and he turned around to Bill, and he says, I get it. He says, I absolutely get it. He says, I couldn't stand being down there. I hated it. Hated every second that we were down there. And he absolutely changed his mind. He says, from now on, any astronaut that we have any kind of question mark over, he says, we're going to stick them in here before they go anywhere near space. And the entire idea was to put them in a steel tin can, a modified mini space station, on the sea floor, look at psychosocial elements, put them through a high up-tempo mission, let them adapt to training, let them do experiments, let them do modified spacewalks, all of the components that would go into a mission, and see how they respond. So at the moment, what we do is we use this environment and this habitat as a training mechanism for the astronauts, and we do it in 2 ways. Generally, the 2 groups of astronauts that end up here is either newly minted astronauts that have had issues. Something didn't go optimally during the training environment. So the astronauts go through a 2-year training process as astronaut candidates, so they may not have been great in the water. They may not have been able to adapt quickly enough. So this gives them the opportunity to go into a real-world mission scenario and raise that lower bar of training up a couple of notches before they actually go into space. The second group of astronauts are generally those that are experienced. They've already flown in space, they've proven themselves, and it's part of a commander upgrade program. So some of the astronauts are those getting ready. It's giving them leadership experience, leading a team in a mission environment before they actually go into space, and at the moment that will be to command the International Space Station. I was lucky enough this last summer, I've worked on this mission for the last 6 or 7 years as both a physician, as the diving medical officer, as a rescue diver, and as a scientist. And this last summer I got the opportunity to actually go down as an astronaut as part of the Nemo 21 crew. This was an incredible adventure that I got the chance to actually go, live, work and see alongside the astronauts, and actually be a part of that mission in a way that I hadn't previously, which was pretty phenomenal. So what I'm going to do is just talk you through some aspects of the mission, what this mission means, why it's important, some of the experiments that we did, some of the nuances, just some of the stories, and then kind of give you a chance to just ask questions about what we did and what's in store kind of for the rest of the program. Okay, that was the wrong button. No, that's really the wrong button. Okay. Don't let doctors touch computers. We're not allowed to press buttons. Okay, so we'll talk about a little bit about the background, a little bit about Aquarius, Nemo, the mission objectives, and then the highlights. So my background. I trained in medicine at UCD, but at heart, I'm a space cadet. All I'd ever wanted to do was go into space, and behind closed doors, I'll admit it, I wanted to be an astronaut. I wanted to walk on the moon. I ended up in medicine, and after a couple of years realized that if I really wanted to do this, if I really was going to pursue this seriously, I had to actually go and change the track that I was on. So in about 2003, the European Space Agency put out a call to all the medical schools in Europe, looking for a fresh injection of ideas in 4 specific areas, not that they were having issues with, but wanted fresh blood as part of the mix. So I submitted an abstract that was based on using ECG, the electrical activity of the heart, that blip line that you see in the hospital, as a surrogate marker for sleep disruption and instability. So we weren't looking to go and replace all the equipment that you would see in a sleep lab. So you've seen a sleep lab. You see kind of the sleep left with the wires coming out everywhere. You have the tube and a whole load of equipment that's just very cumbersome. It's also expensive, and it's even more expensive to get it from here into orbit. An ECG is a readily accessible physiological parameter that is easily attained and can be used for so many other things in medicine that it just made sense that we may not be able to get all of the data like the stages of sleep, but we're not looking for stages. We're looking for quality and disruption of sleep. So I wrote an abstract, it got selected, and I was flown with 30 other students from all over Europe to the European Astronaut Centre for a week. There we got to meet some of the European astronauts, some of the staff from the European Astronaut Centre. They had the head of life sciences over from NASA, and then the counterparts from Russia. I presented, and the head of life sciences from NASA pulled me aside afterwards, and he said, listen, we're looking at something similar to this. He says, NASA's working on a similar concept. I like what you're doing. Go flesh out this idea, expand on it, go and make a presentation, write a white paper, go and present this at a couple of scientific conferences, and let's see where it goes from here. So I followed the man's advice. Over the next couple of years I did exactly that, and then I ended up putting the experiment into this mass European Space Agency database. So every time one of the European astronauts flies, there's a database of experiments that they're able to go in, select experiments from, and actually identify the experiments that they want that astronaut to fly in a particular mission. I was lucky enough that the experiment that I was doing, they needed a student experiment at the time. They liked the angle that I'd taken, they liked the background and the components, and through a series of kind of steps, it went and got selected through shortlisting and so on. So the experiment goes and gets selected. At the time, I have a PowerPoint presentation, I have a white paper. Head of the program rings me. He says, congratulations, I already had a letter in hand saying, you've been selected, experiment's going to fly in ISS. And I was like, fantastic, outstanding. And he says, now, I'm going to ask you a serious question. He says, can you really do this? So I took a minute, I paused, and being Irish, I turned around and said, absolutely, no question, we'll get this done. In the back of my mind, I'm thinking, okay, so we're going to fly an experiment in space in 18 months. That's generally a 5-year process. So they know I'm a student, and we're working on an accelerated timeline. Of course, the European Space Agency is going to go and give me all of the resources that I would need to go and make this experiment happen. So I turned around to my university, and then at this stage I transferred over to engineering in UL, gone to the university and said, well, we kind of need a letter. We can't really take your word for it that you're actually going to be flying an experiment in space. So I went back to the European Space Agency and said, listen, I need a letter just establishing bona fides for what we're doing here. And they were like, no problem. I was like, on letterhead, fancy letterhead, as flowery as you can make it. I was like, no problem. Came back with the letter. And the crux of the letter basically said that the European Space Agency will cover all the costs for this experiment from getting it on the rocket from Baikonur to the International Space Station. So I was like, that's great. What about all the costs up until that? What about all the development costs, all of the testing costs, all the transport costs to get this bloody thing both to America and to Russia, because it was going in 2 separate vehicles? And they're like, well, that's up to you. So that started a pretty long process of finding equipment, and then they came up with another zinger. So the equipment that we decided to use, that I'll show you a little bit later on, was a fitted life monitoring vest. So this was a fitted shirt with all of the instrumentation actually built into the vest itself, so it wouldn't float off when the astronaut was sleeping in orbit, and then a modified recorder for all the data that we were putting on to compact flashcards. The problem was they didn't want one, as I thought initially. So we needed a flight model. Then we needed a backup flight model just in case something happened to the flight model. Then we needed the model that was going to be tested for off-gassing. Then we needed the model that was going to be tested to destruction. Then we needed the model that the Russians needed as a backup to the backup, just in case they needed something else to do with it. And then we needed another model for EM testing. So in total, rather than the one we were going to fly, we actually had to purchase 6 sets of equipment, all of which were €10,000 a pop. Yeah, exactly. My heart sank. So to cut a long story short, my engineer was coming back from a conference in Austria, space conference, and he happened to be sharing a taxi with a guy from Enterprise Ireland. And he was talking to me about the great project we were working on, we were trying to find funding, and the guy turns around and he's like, oh, I work with the Prodex Fund. He says, what you guys are doing fantastic. He says, we need to get you guys funded. Fast forward 2 months, I made €100,000 in funding from Enterprise Ireland and the ESA Prodex Fund, and that literally saved us. We were able to go get the equipment, fund all of the testing, all of the results that we needed. We needed specially made containers and everything else. So it went up, it flew. Tomas Ryder was the astronaut that flew it as part of the ESA Astrolab mission. He went up on 121, came back on 116. Shortly before he came back in around October, I was over in Britain and I met up with one of the flight surgeons from Kennedy Space Centre. Talked to him about what we were doing. He's like, this is fantastic. The first Irish experiment on shuttle on ISS. Like, you need to be there. Would you like to see your experiment come back on the space shuttle? I was like, there's a bear shit in the woods. He's like, well, we can sort this. So at this stage, I've been trying to get over to NASA and to Kennedy Space Centre for years. But ever since 9/11, it's been so difficult to get the paperwork requirements and get past the security onto a federal installation. So you need to know somebody. So he went, signed all the paperwork and said, this is necessary for NASA's mission. They're coming over to support the space shuttle. And we ended up being at Kennedy Space Centre on the 23rd of December 2006 to see our experiment roll back on the space shuttle on the runway, which was pretty phenomenal. At this stage, I'd qualified as a physician. I'd also convinced NOAA to train me as a diving medical officer. I was a scuba diver. Met with the team at Kennedy, both in the biomedical research lab, met with the team on the triage team. They're like, well, we like your background, we like your research. Do you want to come over for 6 months and spend some time with us and become part of the triage team? So I basically went home, walked into the emergency department and said, I quit. And the consultant was like, I don't blame you. And he turned around and he said, listen, he says, your job is here if you ever want it. He says, but I don't ever expect to see you again. So went over, got a badge, got in 6 months, turned into 3 years later. I was lucky enough to support 15 launches and landings all the way to the end of the space shuttle program as part of the triage team. The team that we used to set up was on the very front line in front of the vehicle assembly building. We were the closest human beings to the launch when it occurred so that we could deploy if there was ever a contingency. We had a Department of Defense medical team and a civilian medical team very close by. They had Blackhawks with blades turning all the time, so a really impressive footprint for fire rescue and medical just in case anything happened. I was lucky enough that I became an expert in spinal injuries in the ACES suit. So that's what you can see up here. This is taken during a Mode 4 drill. We used to run 2 significant emergency medical drills every year, a Mode 4 and a Mode 8. The worst case scenario for a launch and the worst case scenario for a landing. So the Mode 4 was effectively if something happened, if something exploded on the launch pad and you had astronauts on the pad with limbs hanging off, severe injuries, there was life and limb at risk. And the whole concept was they would deploy the emergency medical apparatus, they'd turn on the sprinklers on the pad, we'd send in a fire rescue team in these super cool garments with actually liquid oxygen in the tanks because of the risk of burning rocket fuel. We simulated go down in the emergency baskets from the pad to the bunkers, get carried off, let the emergency medical teams do their thing here. And I suppose a little bit strategically, I planned that I was the astronaut that had the very worst injuries. That if there was a decision to be made on a certain astronaut that had to be evacuated immediately, it was going to be me. And it just so happened that that evacuation had to take place in a US Air Force Black Hawk helicopter to fly across Florida. So to say that was a good day would be an understatement. So I was lucky enough to spend a significant amount of time in that ACES suit. The ACES suits were modified pressure suits from the U-2 spy plane that they went and upgraded over the years specifically for Space Shuttle. So you had a cooling garment underneath that then locked into this kind of cooling bag that you carried around, a sealed suit that was all locked in together, and then the suit itself actually connected into the Space Shuttle to connect all of the medical instrumentation that you had on board at the same time. Very cool. They actually used to go and fly these suits in from the astronaut quarters in Johnson Space Center specifically for this. So when you got suited up, you had to be in astronaut crew quarters in Kennedy Space Center, which is a sealed, locked floor of a building, and sat in the chairs that they would use specifically when they suited up to go out to the pad for a launch. So that was really cool. You got a little bit of behind the scenes of what they got to do, and this was absolutely incredible. This is some of my favorite memories of the stuff that I got to do. I was also lucky enough to get into Discovery and sit in the commander's chair on the stack. So you have the shuttle, you have the external fuel tank, and then 2 solid rocket boosters on either side. Basically, solids are there, tank is about to be fueled, shuttle is vertical, and got to sit in the commander's chair just shortly before it went into orbit. So that was a pretty good day. I suppose another little bit of background, I qualified from UL with a doctorate in biomedical engineering, so trying to mix medicine with the technology component. My day job centers around the design and development of next generation medical equipment. We design fluid monitors that predict the fluid changes that could occur not only for spaceflight, but looking at changes for heart failure patients, dialysis patients. We've developed the first generation of a small kind of tricorder-like device, so about a credit card size monitor that is non-contact, non-invasive, that works on the basis of directing a single tone radio frequency into the chest. And based on a phenomenon called RFII, radio frequency impedance interrogation, it has a resonant frequency coupling effect with a moving dipole molecule. So what we actually do is detect the return loss from a signal as it couples with moving dipole molecules, which in the body turns out to be hemoglobin, as blood is being pumped from the left ventricle, that big chamber in the heart, into the ascending aorta, that big large vessel. What happens then is that every time the heart pumps, like so, we get a blip from the change in return loss. That provides us with a cardiosynchronous waveform. We're then able to establish beat-to-beat intervals, which gives us heart rate. From that, you get the undulation of the waveform from impedance that, as you breathe, the actual baseline of the signal begins to change. Then from that, the amplitude of the waveform actually provides us with a surrogate marker for how much blood is being pumped with an individual beat. Now this is important because it has application when you can't use electrodes, when you can't use gel, in situations like spaceflight, pre-hospital care, in ambulances, any kind of extreme environment that you can think of. These types of devices have application, not only for missions like this, but for mass casualties, in hurricanes, where you have mass numbers of people and you only have one medic for every 10 people. How does that medic go and drop multiple medical devices? So we went and designed a system that would then allow the device to actually go and autonomously triage those patients based on universal standards of green, yellow, red, so he could go and actually treat the patient most acutely ill that had life-threatening injuries. The small devices that you see there are small fluid monitors. What we actually did in this case is we modified those devices to actually be able to provide a predictive index for patients suffering from Ebola. So those patients that have been exposed to the virus but were not yet contagious. The way Ebola works is the virus goes and attacks the outer lining of the cells, and what happens is it dumps the water inside the cells, outside the cells. So we had a frequency shift in the way that we monitor fluid, and we were actually able to graphically represent how that change occurred, and we were able to provide about a 6-hour window from a patient that went before they went from basically quarantine but stable to a contagious state, and actually give the doctors a window of opportunity to actually put them into full quarantine, get fluids on board, antibiotics and so on. My night and weekend job, I teach and train combat medicine. I take Navy SEALs, Green Berets, Ranger teams, and we deal in worst case scenarios. So these teams that deal in hostage rescue, counter-terrorism, I get them for 24, 48 hours after they've gone through the workup, and we'll deal in a situation going into a hostage rescue. Then they get attacked. Team leader gets taken out. Then we take out the medic. And then they have to deal with these catastrophic injuries for 24, 48 hours before rescue team or before they can evacuate, and learn how they manage these injuries in a field environment with what they have on their backs and still complete the mission. It puts a lot of stress on these teams, but the whole idea is to raise the lower bar of their training mechanism. On the space front, I'm the doctor for the Vomit Comet. So we get a plane, a modified 727, and fly it in a pattern in the air called parabolic flight. Once before we hit this curve, just the top of the curve, we take the engines and we reverse them. So rather than flying the plane up the top of the curve, the plane actually falls over the top of the curve, carried by its momentum. So the plane is falling, everything in the plane is falling at the exact same rate, and then we get 20 seconds of weightlessness. People wonder kind of about the plane, the injuries and so on. We've had everything from burst eardrums that I'll talk about in a second, but one of the biggest things is nausea. That inner ear, those semicircular canals in your ear that people get when they're motion sick or they're seasick, now imagine that all of the fluid in those ears and in those canals actually starts to float. You have people that within 2 parabolas are literally turning green. They go into a diaphoretic sweat and they just simply can't handle it. And in microgravity, everything floats. I've been on planes where once somebody starts to go, people around them start to go, and I've seen projectile vomiting go across a plane and they're only there for 20 seconds and then it goes splat. So you're trying to go, and we pick people up that they're just so incapacitated that we're in, microgravity kicks in, they're just curled up in a ball. You take them up and you throw them down the plane. Somebody else is at the end, catch them, stick them into a seat, get a wet rag on and hope they just stay where they are. So last year we were actually doing a flight in Florida, and we got to the apex of the parabola just as microgravity kicked in, and we had an emergency decompression. One of the seals in the plane went. So not only do you have people floating, suddenly this big cloud of fog comes rushing through the cabin. Suddenly, because the pilots see it, it's an emergency, they take that plane, engines back on, point that sucker down, and it's diving towards the ground. And I mean going fast. So we're getting people on O2, you girls screaming, 4 people had burst eardrums, and then you had all the stuff from microgravity that was floating just went whoosh, down to the ground. So that was a busy day. That kept me, I had paperwork after that one. Then obviously the Nemo mission that I got to do, so I'm an avid diver. Spare time to spend trying looking for sharks, big sharks, any sharks, sharks that bite, preferably other people. And then this mission kind of was the culmination of all this stuff together. So what is Aquarius? Aquarius is the world's only underwater research laboratory. You can see here on the right hand side. Do I have a laser by any chance?
No.
No? Okay, fingers it is. The back of the starboard side that you can see here down the very bottom, there's 3 bunks, one on top of the other. So very, very small living space. Beside that you have a living area with a galley window, small table that comfortably will sit 2 people, one on either side. Uncomfortably will sit 4 people. You're likely to get an elbow unless somebody's very, very slight. You have all the life support systems there. You have a small kitchenette and sink, small workspaces. Moving into the science locker where we have screen set up, we have a science sink, some more life support equipment. That's where the main bulkhead of the habitat ends. And then moving into that then is the wet porch, where we keep all of the scuba gear, all of the dive helmets, all the wetsuits, and that's where the moon pool is located. So we try and keep a barrier between the wet and the dry, just to make sure we're not carrying water into the rest of the habitat. You can see here the moon pool that we get in and out, so this is how we get in and out of the water. The air pressure inside Aquarius is kept just slightly higher than the water pressure outside. So the air pressure is actually continuously keeping the water out, so we don't actually have to go in and out through an airlock. we can actually just climb in and out of the water, which makes it really easy. You can see up here at the top in the middle, the galley table, and then the large porthole. So you can see the living space. So 6 people living and working in this space. You can see here the science locker, so all the life support and kind of gauges and equipment on one side, and then that little bit of space, and then looking back towards the little fridge on the left hand side here, then down into the bunks. So it's a mini space station on the sea floor. For 6 people to live and work, it's actually fine. And after a day I was like, oh, this feels like home. It was comfortable. It's comfortable if you get on with the other 5 people. It's comfortable if nobody's a pain in the ass. It's comfortable if that's all you're doing. However, we weren't just living there. We were working. One of the biggest things that we found was the conflict in the schedule of trying to conduct different types of science experiments and not take up all the real estate, not take up all the floor space. Trying to do multiple things at the same time, this space became very, very busy, and you'll see some of the stuff that we worked on in a little while. So this is just a good view of one of the aquanauts down underneath Aquarius, and you can see the habitat up on stilts, and then we had these 600-foot long umbilicals that connected us. So the Kirby Morgan hard hat had full audio and voice comm inside, so we can talk to back to the habitat. They can hear us and talk to us, and then it contained life support, so our air supply, and all of the comms went back. This particular mission, the 600-foot long umbilicals that we use were the longest ever, and it's the longest allowed by the United States Navy. They don't actually go longer than that. We have a range of support divers and equipment available to us, so this one, the aquanauts, just preparing to go down or go back up, but we have these scooters made available to us simply because we're traversing large distances with equipment to support the aquanauts at any one time, so the divers, this is a good mission to dive on. So, why Nemo? We talked a little bit about this being a high fidelity or a high quality training environment. We talked a little bit about why it's important for the astronauts and for the leadership components, the stress that we put them on, the psychosocial interactions and team dynamics. It's much better to see a crew member have issues in an environment like this and have interpersonal issues with other crew members in this environment rather than in spaceflight. There have been issues over the years, now not many mind you because they're well screened, but to see somebody crack a little bit under pressure, under stress, in a high up-tempo environment has a very, very interesting but detrimental component to it for missions like this. So there's a real good example on Mir where there were 2 cosmonauts, I think up there for about 6 months. For most of those 6 months, the 2 cosmonauts lived on opposite ends of the Mir space station, didn't see each other, didn't talk to each other, didn't interact with each other. And it caused some pretty significant problems, obviously, during the mission, that they just did not get along. They hated each other, was the bottom line of what occurred. We also get the opportunity to test new spaceflight hardware. So the EVA, or the Spacewalking Tools Department, is often heavily involved with this mission of trying and testing their technologies, and then looking at spaceflight procedures. What works, what doesn't? What are we missing? Does this procedure work for spaceflight on certain pieces of equipment? Do we need to adapt or change it? Much easier to do that here, but it's great to get the feedback of high-level operators like astronauts before you actually send it into space, because then you get one shot. Once it's up there, it's up, and you can't change anything about it. The other opportunity is being able to do a significant amount of scientific research. Medical research is one of the areas that really benefits from interaction in this type of environment simply because of the level of data that we get back. One of the things that Nemo and the Aquarius habitat has been able to show over the years is that the immunological and physiological profile that we get from crew members as part of this mission almost mimics exactly the same profile that we got during a high up-tempo space shuttle mission. So immunology, levels of hormones, cortisol, all of these different components that we look at in what's called biomarkers are mimicked on board Nemo very, very closely to what we found on spaceflight. That's one of the ways that we know that the stressors in the environment that we're exposing these crew members to are replicated so closely by this mission as it was on spaceflight, and why it's so valuable. So analogs come in 2 flavors, environmental and mission. The environmental conditions are a little bit different with Nemo with the other habitats. So we have habitats up in the desert in Utah. We've habitats up on Devon Island in the Arctic, and then we've mission the high seas that just finished out in Hawaii. The one thing all of those missions have in common really is that if you have a bad day, if you're pissed off, if you're angry, or if there's an emergency, you can walk out the front door. Nemo's different. When we go down, after about 24 hours, you are officially certified as an aquanaut. You are living under pressure at depth on the seafloor. It also means that your body is now completely saturated with nitrogen. It's called saturation diving. One of the biggest problems and risks with scuba divers is decompression sickness, or what we call the bends. Divers go down underwater for a significant period of time. When they come back up, they do a safety stop. If they stay down for too long, they actually go into decompression diving where they have to do scheduled stops. Take this to a whole new level. After 24 hours, all of the body's tissues at that depth are now completely saturated with nitrogen. The bones, the muscles, the soft tissue, the fat, everything else. If we were to go after those 24 hours from the seafloor back up to the surface, all of that nitrogen would expand in all of those tissues all at the one time and could cause a catastrophic incident of the bends or decompression sickness that could potentially be fatal. We could get bubbles that would travel to the brain, just in the joints, cause excruciating pain. So after those first 24 hours, what effectively happens is we must go through a 15-hour decompression or recompression to come from the seafloor back up to the surface. So what happens? At the end of the mission, we actually go and seal the bulkhead doors of the habitat, and then we go and take it and we actually raise the pressure over 15 hours from the depth of the seafloor back up to the surface. The habitat doesn't move, it stays on the seafloor, but we actually raise the pressure. At the end of the 15 hours, we'll dive the habitat back down to its normal pressure, open the door, and then you've about a 15-minute window for those that are leaving to go get on your scuba gear and actually dive out back up to the surface. So that gives you kind of an idea. The 15 hours is important because it's almost the exact same timeline that it takes that if you had an emergency contingency on board the International Space Station to get from hatch to ground. It's almost the exact same timeline, and that's why kind of this is so appealing. We also have the ability to go and do spacewalks or EVA on the seafloor. So every second day, 2 aquanauts are on the seafloor. We spend about 7 or 7.5 hours traversing on the seafloor doing different types of experiments. The lab and the layout of the habitat are similar to a node or a module for the International Space Station. We also have a highly structured timeline with the same constraints that you would see in a spaceflight mission. So during this mission, we actually bring in 4 or 5 different NASA centers. We've had teams in from Canada, from Japan, from not Russia yet, but the Europeans as well, with a big footprint. And this is treated like effectively a mini space mission with all of the constraints and all of the support necessary to make it happen. Nemo has both. So why Nemo? We talked a little bit about the training environment of getting astronauts ready for spaceflight. We talked a little bit about the testing of new technologies, procedures, and so on. So at the moment, you heard in the last talk, we have one of the greatest constructions that mankind has ever put together. The greatest orbiting laboratory going above us right now, doing phenomenal research. The research station will probably be there until about 2028, but that's not the end goal. Nobody ever said, I want to build a space station and stop. The end goal for most people, most space agencies that you would ever talk to, is to get to Mars. Now, one of the biggest problems is NASA has been talking about getting to Mars in the next 20 years for the last 60 years. So we can probably keep pushing that timeline out. But at the moment, the date for going to Mars, for putting humans on Mars, is being talked about in around 2030. Now, one of the biggest problems is political will, funding, kind of the political landscape. If you've one president that wanted to go, the next guy probably isn't want to go because he wants to change things. So the diagram that you have up on the top right hand corner is NASA's current vision of a journey to Mars. One of the big internal NASA jokes at the moment is the diagram goes all the way to Mars. The funding only goes halfway to Mars. So what are you going to do? But we also have the private space industry, the commercial industry. Elon Musk has this grand vision of getting people on Mars sometime in the mid-2020s using current technology. I'd be hard pressed to find anybody that's really going to bet against Elon Musk. He's a modern day Tony Stark and really seems to accomplish so much when he puts his mind to it. And we also have the advent of new vehicles. At the moment we're reliant on the Russians, the Soyuz, to get our astronauts from ground up to space, which is kind of a hard pill to swallow. Soon we're going to have two commercial companies. We'll have Boeing and SpaceX that are going to be providing their own capsules that will be made available, and then we're also developing the Orion capsule. You have Red Dragon, the Red Dragon concept from SpaceX that they're hoping to send a mission to Mars. But we also have the commercial space industry. So I think we're really at a tipping point for space over the next couple of years that I think we're going to see a paradigm shift. We have the likes of Virgin Branson and Virgin Galactic. They're going to be taking tourists up to the very edge of space, just past that 100-mile marker, to be able to get up out of their seats, see the curvature of the Earth, get out of their seats, float around. The only problem with that is what most people don't realize is it's going to be for 2.5 minutes. You're going to pay $250,000 for 2.5 minutes of a nice view and floating around. So I would say stick me on the plane any day. Now you heard in the last talk, this one kind of took my thunder, but like we have some phenomenal photos that have been taken of Ireland from the International Space Station. So you can see Ireland from Space Station, but you can also see Space Station from Ireland. So you have the orbital ground tracking software. So what you can see up here is the different tracks of ISS, some of the satellites, and the Soyuz when it docks, and then the different ground tracking stations. So you can see the massive footprint that the ground tracking stations in Russia and that they have. One of the only reasons that we can actually see the ISS in Ireland is because the Russians are involved. Had it just been the Americans like it was originally planned, the track would have been much more conservative just to spend as much time as possible flying over the United States. So we actually have the Russians to thank for that. And when you actually watch it, it's literally, it takes about probably somewhere between 5 and 7 minutes depending, but it's literally the brightest star in the sky that doesn't fade and just moves across the sky. It's actually on a clear night. It's a pretty spectacular sight to be able to see. So there's a variety of different software you can use. Daniel talked about one. ISS Live is another good one. They get an Android and iPhone where you can actually show the track and the video in a split screen at any one time with one of the external cameras. So NASA has done a significant amount of work over the years in preparation for either going back to the moon, which we think that the next administration might actually pursue because there seems to be a great international inclination to go back to the moon. So all of the work that was done with the Apollo missions. We have 3 rovers on Mars at the moment: Spirit, Curiosity, Opportunity, doing different types of work, different types of exploration, looking for little green men, looking for water, whatever else. We've had 21 NEMO missions that have built up an extraordinary level of experience in this type of environment. Different types of research and technology studies, and then other analog programs. So there's BASALT, there's RISE, there's HISEAS, there's HERA, there's all kinds of funky acronyms and names, but the bottom line is there's a wealth of experience that has been built up in these types of operations. So Scott Carpenter was the first aquanaut, astronaut, whatever you want to call it. There's different abominations out there. He was one of the original Mercury 7, so really one of the original right stuff, and he was the second American to orbit the Earth after John Glenn. While he was still an astronaut, he was still active US Navy, he went and started diving and then pulled out of the astronaut corps and then ended up living in Sea Lab 2 for about 30 days. So he was the first guy to live both in space and underwater. As of now, in the last mission that we had, we've had Reed Wiseman and Megan Benkin, who were my 2 commanders, became the 49th and 50th people to ever live in space and live underwater in a lifetime. So 50 people, it's not a small number, but it's a pretty exclusive group. So this is my crew. We had 6 aquanauts, and this is us just after diving down from the boat just before we went inside Aquarius for the first time, and then we have our 2 habitat technicians. So at any one time, there's 4 aquanauts inside the habitat, 2 habitat technicians that are there to look after the habitat, keep an eye on us, make sure we stay out of trouble, don't break anything, and don't sink or flood the bloody thing all at the one time. This is us again. We come around the corner. So this is the goofy action shot that a group of astronauts wanted to do before they went into the habitat. You would not believe how hard it is to get 6 highly functioning people underwater to do an action pose all at the same time and not look like a bunch of idiots. Some of these are record-holding divers, experienced astronauts, and we all look like morons. The rest of the crew hates this photo. I love it because it just demonstrates how badly wrong a photo can go. So this is the crew. The top left-hand corner on the boat before we went down. Then Hank and Sean came out. So these two guys were interesting. Sean was a young commercial diver that had screened as a Navy SEAL years previously. Hank is the US Navy's highest ranking master diver. He is the most experienced and most senior diver in the US Navy when he retired shortly before this and went to work on Aquarius. The crew up here, this is the very first day of the mission, everybody came down. This was kind of cool. The very first day of the mission, we actually got the opportunity to do a live link up with the International Space Station. So we had Jeff Williams and Kate Rubens on ISS, living in space. We had us down at Nemo 21, living under the sea, doing a live link up. So we got about a 30-minute link up through Mission Control in Johnson, and we got a guided tour of the International Space Station with Kate, who had just arrived a week previously. So she's not experienced. She still hasn't adapted to flying in orbit, so she's banging around, bumping into the walls, trying to hold the laptop, do selfies all at the same time, and it's hilarious. One of the good things is we had met Kate previously at Johnson Space Center, and just before she left to go back to Russia, and then she had also been a Nemo crew member years previously. So she knew what we were doing, knew the excitement level and everything else, which was pretty cool. The bottom right hand corner here, you have Megan Benkin on the left, Reed Wiseman on the right. Megan Benkin was an oceanographer who actually went and defended her PhD while she was an astronaut. She got a lucky set of coincidences that actually allowed her to qualify as an astronaut while she was still a student, which is very unusual. But she was one of the astronauts on board STS-125. She was actually the astronaut that was the robotic arm specialist that retrieved the Hubble Space Telescope, which was a pretty extraordinary mission in its own right. Then Reed Wiseman was part of Expedition 4041, who was on space station for 6 months, about a year and a half, 2 years ago. The guy in the middle is Chris Cassidy. He's a former Navy SEAL. He flew in the space shuttle, and he flew on the International Space Station. I hate this guy. This guy is the epitome of a modern day, effectively James Bond is what his crew members called him. When he got a call to be an astronaut, he was leading teams in the mountains of Tora Bora chasing the Taliban. And his commander got the call and said, "Hey, you're going to be an astronaut." He says, "I don't have time for that, I'm chasing Taliban." And basically disappeared back into the mountain. I was like, so he's cool. An extraordinary background, great guy. And just before this, he had just taken over as the new head of the astronaut office, actually. So what did we do to prepare? We had months of experiment preparation for this mission. We had a range of 20 to 30 different experiments, a lot of them human related, so they required IRB consent. So a lot of time and effort was put into that. Then we actually got the opportunity to go and train and do about a week to 10 days worth of training with the astronaut at Johnson Space Center. So we got exposed to some of the experiments, but one of the best days that we had was towards the end of the week, where we had to do a swim test. Now, at Johnson Space Center, there's only one pool that's available to do a swim test in. That pool is called the NBL, the Neutral Buoyancy Lab. The Neutral Buoyancy Lab is one of the world's largest swimming pools. It's about 4 stories deep, and it has a full-scale mock-up of the International Space Station actually sunken down into the water. So we ended up doing a swim test, getting ready for Nemo, while swimming over and back 500 meters across this gigantic mock-up of the International Space Station in water that was literally crystal clear. It is the slowest swim test in history, I can guarantee. Nobody touched the wall, like literally within seconds of the allowable time, because we didn't want to get out of the water. And this is a photo taken with Paolo Laspaldi, who's the European astronaut. So we actually have a launch going on tonight, so tomorrow's Pesquet, anyway, it's French, tomorrow. And Peggy Whitson, the US astronaut, are actually just launched. They're going to launch at 8:20 tonight. And Paolo is actually the back for that crew. And he'll actually launch in I think 3 months' time, give or take. After that, we ended up getting down 5 pieces of later. And then we did another
long session of experiments and all the different ones of getting ready and trying to just get up to speed with science. So the why I love motion matches. This is me 21 around once. So my commander is a little gambler. He likes to down a little money and so on. So 21 being blackjack. We needed a show fancy cool logo that kind of NASA we wanted, and then we wanted the cool logo that we wanted. So we got the diving helmet, we got the queen and the ace for blackjack, and then we needed something to be able to give to personnel that had supported the mission that were there with us as a token of our appreciation. So we said, well, why not make poker chips? Rather than doing a mission coin or any of the usual stuff, so the commander loved it. And then the other component was we needed a crew model. So this was the first time in Nemo history that we'd actually taken a crew, split them in two. So we had 2 crew members, Megan and Matthias, who were going to be down there for the entire stint, 16 days. Myself and Reed, who were going to be down for 8 days. Then 2 more crew members, we were going to go up, they were going to come down. So the motto became double down or split, which is actually a blackjack term, which we were actually very proud of, and again, another goofy reference. So, I'm a scuba diver. I'm a diving medical officer. The diving that we did as part of this mission was completely different. We needed to go and get trained on these Kirby Morgan stainless steel hard hats to replicate the experience of not only working within a spacesuit and a space helmet, but to provide all of the communication and the video that we needed. So we had to spend about 3 days being trained on these helmets, both in classroom and diving on the seafloor to really get used to them. So this was interesting. I don't suffer from claustrophobia. I'm not afraid of tight spaces. I've been cave diving. However, when we were sitting in the classroom, first of all, you go and you put on this neck down, it's pretty tight, steel neck down with neoprene collar, you go and pull that on, then you get the helmet, put this helmet on, and the helmet slides down, and you're like, oh, okay, it's cozy. And then you go and get the neck down, put it up, and you close the neck down, and suddenly it seals. And then you're like, didn't expect that. Didn't expect it to be just quite as tight as it was. So sitting in the classroom and I was like, yeah, I got this. Like, I'm fine, I'm a diver. Like, I don't suffer from claustrophobia, it's just a new experience. So we were great. We got out and we're on the boat and you get out and you get to dive and you get to go down and you go through the different procedures. One of the biggest concerns and biggest risks with this mission is we're in saturation. So no matter what goes wrong with that helmet on the seafloor, we can't come back up to the surface. So we have a series of valves and turns on the Kirby Morgan that allows you to direct air from the umbilical back to the aluminum tank or the aluminium tank that's on your back with a reserve air supply. So it's about 20-minute supply. So if something goes wrong, you have enough air to go and leg it, because we're on the sea floor, back to the habitat and get back in. You also have a pneumo hose, that yellow hose there, that works as a depth gauge, but they can go and turn that hose onto free flow and you can get that up inside your helmet, or you can use your buddies and do the exact same thing. One of the biggest risks to aquanauts for panic is what happens if that helmet floods. What happens if that helmet, and you're inside it, actually fills with water? So, it's all well and good to talk about the theory of your helmet filling with water, and then you go and you sit down and you go and you turn the valve and you'd empty it. But when the risk of actually shooting to the surface could potentially be fatal, they need to be able to make sure with an instructor present for the first time that you can actually do it. So how did they do that? They go and they get you to go down your knees. Then they get you to go and lie back. And you tilt your head back and you get that neck down and you open it. And what happens underwater when you open up a dam? The entire thing floods with water. And I can tell you, lying on my back, opening that dam, and the entire helmet flooding with water and you inside, was the first sensation I've ever had of that mammalian reflex of drowning. It was scary. And I went and I not panicked, but I was anxious. And I went and got onto my knees literally as quickly as possible, went, turned the valves, got that, and I was relieved to have that helmet empty. And it was very significant. It was one of the only times that I've really had a level of anxiety doing training, and I didn't want to repeat it. I thought I'd be fine, but I was like, yeah, once is enough in that one. And it was a lesson learned. Some of the other training that we did on the sea floor was learning how to use some of the navigation equipment that we have. We get a lot of stuff from the US Navy. This device actually allowed us to traverse different waypoints that I show you in a little bit on the sea floor, out from the habitat to different points in the coral reef, mimicking how you would go and actually lay out some of these waypoints during a mission. I talked a little bit about topside support. We had 4 different NASA centers bringing in an entire footprint that supported mission control. We had Capcoms come in from mission control from Johnson and the European Space Agency, and comms come in from KSC, and a full internal network that allows us to communicate directly with the habitat, with the aquanauts, and transfer everything we needed back to the core NASA centers. This tool is called Playbook, and was actually one of the most interesting components of this. On station, they have a tool called Optimus. Optimus takes an individual astronaut's timeline and breaks it down over the course of days and weeks, and it basically gets filled up all the tasks he has to do. Optimus goes and calculates inconsistencies in the timeline for activities that need to occur simultaneously with the rest of the space station. So there's certain things that need to happen before a docking. There's certain things that can't happen during a docking. There's certain things that they'll need to do before, during, and after a spacewalk. Optimus goes and calculates all of those. This mission uses Playbook because we have multiple crew members that need to work in tandem. We're not sitting down in the water looking at the fish all day long. Your individual day is literally scheduled from morning till night in 5-minute increments. And then you have this thin red line that's moving consistently all the way throughout the day. If that thin red line moves over an activity and you haven't completed it, the activity turns red. And you would not believe the level of stress to see that little red line move along your day and multiple red boxes appearing because you haven't completed it. Then the white space that you were going to use to actually eat your dinner at the end of the day, or when bedtime came, you're still working. You have multiple teams, 20 to 30, depending on you to go and complete those scientific objectives. They spent the last year preparing for this mission, and you're the operator, trying to go and make sure, and it may not be your fault. It might be the blue screen of that with Windows. The software may not work. Somebody may not have actually gone through the bloody procedure correctly, topside. A good example would be when I show you the coral tree farm or the coral nursery that we built. The group topside were using PVC to build it. They hadn't actually gone and drilled the holes and gotten the little bits of PVC out before we took it down underwater. So we actually had to go manually each time and drill out the hole of PVC underwater, which just added a phenomenal amount of time to the task that we needed to do and literally screwed our entire timeline. We have an excellent platform of support divers that support us and tend to us underwater to make sure that we're safe. Tend the umbilicals that we're carrying behind us to make sure that they stay above the coral reef, and then bring down the tools so they'll set up our tools and everything that we need for a day's diving from the boats in the morning, bring it back up at night time, retool it that night, and then rehash the next day. So a really good group. So I'm going to talk a little bit about some of the internal objectives, some of the science that we did on the inside. As I said, we had about 20 to 30 different experiments, and then some of the stuff on the outside. So this is our EVA console, EVA spacewalking. When you do a spacewalk outside the space station, there's always an astronaut sitting in mission control on comms with the astronaut, talking them through the procedure. Okay, step 241, now 242. Put your hand here. Okay, this tool. Okay, beware of this. Providing constant feedback for all of the training and mechanisms that they did. One of the big things that we did on this mission is we operated for the latter half of the mission under a time delay. If we go to Mars, we are not going to have real-time comms. So we simulated 15 minutes for comms to get from the habitat back to Earth. This was a simulated mission to Mars, and then 15 minutes back, so a 30-minute comm delay. So you had all of these screens ranging from the messaging tool back to mission control, the real-time location analysis of the aquanauts, the 2 video feeds, different types of data. Then in the bottom right-hand corner, you had data presenting life support. So one of the biggest things for a spacewalk is not the work capacity of the astronaut, it's actually your life support. How much O2 do you have left? How much CO2 have you built up? Can you last longer with the limited supplies that you have? They went and actually spent time designing software to put up false readings to make sure that you're always scanning this area at any one time. So you can imagine that for 7.5 hours, you're sitting here monitoring all of these screens, taking the science notes, communicating with science, communicating with the mini mission control, relaying that all back to the aquanauts and making sure all the procedures and all the goals are being met for that day. This was my drinking from a fire hose moment. The astronauts that sit in mission control and that have flown are already familiar with this setup. They know what they're doing. They know how they're doing it. Here you see Reed sitting with the HoloLens goggles that we brought down with us, providing additional procedures, feedback, and just-in-time training for some of the components that he was doing. So you have aquanauts on the seafloor that have flown in space before, very experienced. You have a 40, 50-person mission control back on the shore, Capcoms that oftentimes sit with the astronauts, engineers that know exactly what they're doing, and you. You're the one guy that talks to everybody, and for 7.5 hours, you get a flood of information that you're trying to make sure that you're not the one guy that screws up. Because if you miss a beat here, everything starts to deteriorate afterwards. The timeline slips and the objectives get missed. When I got up from this the first time, I was absolutely mentally exhausted. The same day that I did that, Megan Benkin, who was my crew member for diving and EVA, she came over one day because she's doing a completely separate experiment. She's a 7 hours worth of DNA processing to do. She comes over, taps me on the shoulder, says, "How you doing, Mark?" She didn't even wait to get the answer. She just walked away. So I was literally left to my own devices, and this was grueling, but one of the best learning experiences I'd ever had. We then tried it with 2 people, actually later on in the week, to see could one person handle all the workload and just how much benefit was it to have 2 crew members doing this work at the same time. DNA sequencing. This was the first time that DNA had ever been sequenced underwater. Every crew member did it. It was about a 7-hour process. You had 40 pages worth of procedures. You had 30 different reagents, some frozen, some at room temperature, and this was a very finicky, delicate procedure. One of the reasons that this was important is that we were actually fine-tuning the procedure that Kate Rubins was actually going to use on the International Space Station about 6 weeks later. So I was the first guy to do this, so I was very conscious of getting this right. So I'm 3 hours into the procedure. I'd gone and gotten the mini PCR, the polymerase chain reaction machine, ready to go and take the samples. I prepped everything. I'd been very diligent. And this little mini PCR machine that's at my left hand, you go and take that, you plug it into the computer, you put the reagents in, and you start the software. Did all of that, software started, computers going. I'm like, great. Mission control, mini PCR machine, working away. I can see the screen. About an hour later, I get a message. And it says, "Mark, did you turn on the mini PCR machine?" I was like, well, funny enough, I don't actually remember turning on the machine. And I went over, and on the back, there's a little black button that says on and off, and lo and behold, the button's off. So I'm like, shit, damn it. There's 3 hours of work literally down. I was like, can we go? Can we turn this on now? And they're like, no, the sample needs to go back up on the last boat that's going this evening. We've just lost almost an hour and a half. It's not going to work. The reason they went and sent that message is the people that had designed the experiment went back and looked at their own procedure. I had been so diligent in going through this procedure, and I went back through it, and lo and behold, what step was missing? Turn on the bloody PCR machine. They'd actually written the procedure and forgotten to fill in the step of turn on the machine, which turned out to be a massive fault on theirs. So my commanders pulled me aside and listen, it's not your fault. You followed the procedure exactly as it was laid out. You are not expected to step outside this procedure and do anything else. So I followed the procedure, but common sense had gone out the window. But they actually went and changed the procedure and made sure they had double-checked it before they give it to Kate Norbert. Because if she had gone and done the same thing, the experiment would have been screwed, and she literally would have lost half a day's work just trying to get this underway. So that was a learning experience as well. This is Megan doing the exact same thing. So you have these little mini cartridges here that were very, very finicky, and plugging it into this mini ion DNA sequencer. But the cartridge that you can see there was so prone that any tiny little drop of air that was introduced to that when you were pipetting liquid was going to screw up the entire analysis. So it was just so prone, and we were wondering, we actually asked them to go and simplify the entire setup for Kate because we just felt it was too complicated for her trying to float around and actually do the fine movements that were going to be necessary. One of the biggest issues with spaceflight is the problems that we encounter due to microgravity. Muscle atrophy, bone density loss are some serious issues. So the astronauts on the International Space Station at any one time must exercise for 2.5 hours every single day. But on ISS, they have these massive racks for basically lifting weights. They have a treadmill that they can run on. We are not going to be able to provide that level of equipment and just don't have the space in a little tiny capsule that's going to be going basically to Moon or possibly onto Mars. So what do? We need to be able to modify that. So this is Med2, a miniature exercise device. So you can see the size of it here. It's not very big, but it's bloody heavy. It has software and it has a series of servo motors inside that can basically change it from an aerobic to a resistive machine. So at the flick of a switch, you can basically go to a rowing machine to a machine that will provide resistance where we can do deadlifts, we could do squats, and so on. In theory, it sounds great. In reality, this was a royal pain in the ass. This thing did not work accordingly. You had to go, you had to provide thresholds, you had to personalize it, and we spent more hours screwing around with this trying to get it to work. I think at the end it worked a whole lot better, but the whole concept that I talked about, the thin red line, and moving and not getting stuff completed, this was one of those experiments that caused the entire timeline to shift in the wrong direction. One of the other things that we did is tested an EVA swab tool. So one of the biggest things is what happens when we send a vehicle beyond low Earth orbit and it gets exposed to something on the outside. How do we go and sample it? How do we go and find out what it is? How do we go and take those samples, retrieve them correctly? So we went and tested just a brand new swabbing tool. We didn't do it on the outside, we did it on the inside, took a series of swabs, just locked it back up and then sent it back to Johnson Space Center to let them actually sequence and test the swabs and see what level and see what they actually found and see did it actually work. HoloLens. This was one of the more interesting applicable things that we actually got to do and also one of the most entertaining. So the HoloLens is Microsoft's brand new 3D holographic goggle concept. You go and put on the HoloLens, turn around, and it will go and map in 3D the entire room before you. You can go and throw up the window screens right in front of you and actually go and take them. So you can go and take your word processing screen and put it over here. You can go and take your control panel screen and put it over here. If you turn, if you've attached it to either wall virtually, it'll actually stay there in real time. Space Station is huge. It's been up there now for almost 20 years with different crews, all bringing up different materials. We've had different stowage, we've had the Progress, we've had shuttle, everything. It is packed full of stuff that nobody knows where it is. We have nodes, we have modules that are like 3-4 canisters deep. One of the biggest things is trying to find anything is just a huge time waster. So one of the things that we're trying to do with HoloLens is figure out a mechanism of barcoding everything that we can and then linking that into the HoloLens so you can fly through Space Station looking for something in particular. It will tell you where it is, where it's been, where it's supposed to go, and any other details and directions that you need to actually go and find it. It's great in concept. We went and tried practicing this concept, getting it ready for Space Station and putting away these blue Nomex boxes in different areas in the habitat. The problem was that when you get to a window, it actually reflects the 3D holographic screen that you're trying to work on. When you have two people wearing a HoloLens at the same time, it'll actually go and mix up the two screens as you're trying to work amongst each other. So this actually became very, very frustrating for the crew. So Reed Wiseman is a bit of a wild card, and he's a joker, and he doesn't like doing things that he thinks are a waste of time. So one of the things that Reed did was, before we went down, he went and smuggled down a box of Lucky Charms. According to him, the token leprechaun on the mission must have a box of Lucky Charms, and they were sitting on my bunk by the time we actually went down. So it became a running joke, actually doing this experiment, that we have several photos of this experiment being done. We have 4 good photos, actually, in fact. There are 40 different photos of using the HoloLens to stow the Lucky Charms in every single area of the habitat that you can imagine. Because they did it as a laugh, because it wasn't working. NASA became extremely irritated because you can't go and put pictures of astronauts stowing Lucky Charms on a mission all over the internet. It just doesn't work. And so I actually got heat for that, even though it wasn't my fault. I hadn't brought them down or anything else. Last year we actually used the same goggles for just-in-time training for doing advanced medical procedures, for using an ultrasound and some other medical equipment. So we're still looking at the adaptability of this type of technology. Mobile PV was another technology set that we were using for just-in-time training. So you can see here that you had the wrist-mounted display, you had the larger tablet and the smaller tablet, all providing you with the ability of these detailed procedures, and then you the ability to go and call somebody in mission control through the little camera. You can see them, they can see you, and you would actually go through the procedure with that just-in-time component and also help. So the first version of this technology is currently being used on station. It sounds great in concept, but all of these three devices were supposed to link at any one time. You were supposed to be able to call up a video on one, do the procedure on another, flick backwards and forwards between the two, jump up to somewhere else and tell it what to do. And for anybody that uses a smartphone, which is everybody, it just doesn't work like that. So this became a royal pain. Now they are working on it. It is being done on station, so we'll see where that goes. This was Casper. This is the experiment that we flew on station a number of years ago, the sleep experiment. So you can see the fitted vest with a small data recorder in the pocket. Went up on STS 121, back 116, the Astrolabe crest, and then the Casper mission badge. You can see here that this is a breakdown of a night's sleep, and the entire component was astronauts suffer sleep disruption, the excitement of launch, high stress levels, the high op tempo, 16 sunrises and 16 sunsets every day, microgravity. The rising sun is a zeitgeber. It is the #1 in training factor to make sure that everybody can live and work in a 24-hour day. That means that the rising sun resets our body clocks to a 24-hour rhythm. That's why people living in mines, people living in the Arctic Circle, after a while begin to develop issues. First-time astronauts do seem to have significant issues with their sleep patterns, so we give them artificial melatonin. Every astronaut tries out a variety of different combinations of sleeping tablets to see what works best for them, to make sure that they're not zonked, and if they have to get up during the night, respond to an emergency, that the medication hasn't basically dulled their edge. This spectrogram gives the ability to actually map the quality of a night's sleep and actually detect any interruption in that quality throughout the night, or look at any kind of intervention that we might employ. The biggest causes of sleep disruption that we saw during shuttle were changes in noise, vibration, and temperature. This spectrogram gives us the ability to actually go and align this with a mission log or with the environmental log and see if a crew member had a bad night's sleep, did it actually go and relate to a change in environmental conditions. We've also gone and adapted this technology into a wearable small sleep monitor that can be used in domestic medicine for patients with sleep apnea that don't want to go into a sleep lab, that can actually be used at home. One of the other significant areas that we do a lot of work in is telemedicine, trying to detect changes in crew members and monitor their health status from the shoreline by a physician or a flight surgeon, and then taking this technology, not only applying it to spaceflight, but looking at application of this technology for increasing access to care for conventional medicine, looking at people living in remote areas, trying to find ways to keep patients at home, monitor them at home, stop them going into emergency departments and not ending up in hospitals unnecessarily. So this is one of the key areas and one of the areas that I work in on a daily basis. We did a lot of work in what I call telomere degradation and epigenetics. So this was pretty interesting. And it follows on from some of the work that we did with the group that did similar research on the International Space Station. When you have cells in the body, cells divide. And built into the chromosomes in the cells, the cap on the end of the chromosome is called a telomere. Every time the cell divides, that cap gets a little bit smaller, up until it becomes basically a nub end on the end of the chromosome. When that cap gets down to a nub end, rather than dividing, the cell goes into what's called apoptosis. The cell effectively dies. This leads to cellular aging. This is the aging process. Now this has implications for not only aging, but a lot of other diseases. Parkinson's, Alzheimer's, Duchenne's muscular dystrophy in children. One of the other big components of this is, if we send crew out beyond low Earth orbit on a 3-year mission to Mars, 9 months there, 9 months to get back, they will be exposed to potentially extremely high levels of cosmic radiation. It is hypothesized that the damage that could occur on a genetic level and to telomeres as well could lead to extremely severe sequelae later on when those astronauts come back, if they ever came back. That's not a risk that we're willing to take with these crew members. We want to get them as healthy as possible before they go, when they're away, and when they come back all at the same time. So what we went and did was monitored the telomere length before, during, and after this particular mission, and then we've also pioneered a concept of introducing a Trojan horse molecule into human DNA that will actually go and regrow the telomere length. We're looking at this for application to spaceflight and also looking at application for the likes of Duchenne's muscular dystrophy. Epigenetics looks at the change in the expression of gene and the genetic code due to exposure to an environment rather than actually changing the code itself. So we did a lot of work in these areas. The Jedi mind trick one was when you mention genetics to NASA in relation to astronauts, they lose their minds. So it actually took us months and months and months of just trying to convince the IRB at Johnson Space Center that we're not actually altering astronaut DNA, we're not taking their DNA, we're not splicing it or anything else. We're just looking at the changes, but you think for a smart organization, they'd have a little bit more common sense. PSAP, working in conjunction with Johns Hopkins, we looked at changes in the inner ear and vestibular function. And then 2 missions ago, we did a significant amount of work with the Raven robotic surgical unit, where we actually took a team in Duke University, implemented a 3-second delay, and they did different surgical techniques underwater, basically mimicking the requirements of what would be necessary to do robotic surgery on a mission in space if the need ever arose. So we talked a little bit about saturation diving, the risks involved in this type of habitat. We talked a little bit about the 15-hour kind of recompression necessary. So this is the bunk area. You can see the sick astronauts in their bunks, and then for 15 hours we went on and off an O2 protocol to bring us back up to the surface and bleed all of that nitrogen out of the tissues. But what are the other risks? You have the risk of trauma. So if you get a tiny nick or cut down in this humid, hot kind of environment, there's bugs everywhere. The ability for those bugs to get in, the risk of infection is actually very severe. Trauma. If somebody breaks a leg or breaks a limb down there, or even anything, even something more mundane than that, it's very hard to treat, and then obviously you can't bring them back up to the surface. The psychological component. Putting 6 alpha hard-charging personalities down into a little tin can on the seafloor on a high up-tempo mission is bound to cause some kind of friction. We were lucky in that I had a great crew. There wasn't one bad day, one bad moment amongst any of this. Marine life. During the mission, we'd 5 bull sharks that appeared after about, I think, 3 days. At night time, they'd literally be right in front of your face in the window, basically chewing on fish. One of them was about 12 feet long. One of the days during the mission, when I was actually up and I was a rescue diver, we actually had one of the large bull sharks actually go and buzz one of the aquanauts underwater, and we actually had to pull them in off the sea floor because we thought he was getting a little bit friendly, and just in case he wanted to just have a taste. So we'll talk a little bit about the exterior objectives. So we talked a little bit about getting in and out through the moon pool. So you can see here, I'm getting out, you jump down from platform to platform. As you climbed out, you had a minimal amount of weight on. So from this here, all you needed to do was sink, even if it was slowly. So you could literally jump from platform to platform and could jump 5 meters into the air underwater without any kind of problem whatsoever. It was fantastic. You go down and jump from this platform down onto the ground, and then we go and do the proper way out with about 40 pounds of weights into those weight vests. See here the platform down onto the seafloor. And this is Sean. So as I mentioned before, Sean was a commercial diver. And this guy was an animal. For 16 days, he spent 8.5 hours on the seafloor every day. He was the first guy out and the last guy in, and then tended all of our umbilicals, fixed them all, bungeed them up, and he was phenomenal. The EVA tool prep, we had rescue divers that brought down all of this staging area with all of our equipment for a given day, staged it on the seafloor, set it up before we set up, packed up in these little carts, and then went off on our traverse down off the seafloor. During EVA, we had a lot of gear with us. So you can see here the trolley that's loaded up with equipment, the coral sampling tools, the reagents, We had a tool belt with a hammer, all of the tags that we were going to need, the EVA toolkit for testing different tools from the spacewalk department. Then we had a tablet that actually gave us access to all of our procedures and all of the other different components necessary. We had so many procedures, so many different tools that required a very set level of procedures and understanding that it had to be loaded onto tablets that we took with us, and then the underwater navigation equipment. The underwater navigation equipment you can see here laid out kind of a template like this with the different gradients. You can see Aquarius up at the top there, and then all of these different waypoints are laid out in different zones that allowed us to go and traverse. These different zones allowed you to go and zoom in on a given day and then follow a specific track through specific waypoints, and then at each waypoint you were given your objectives to make sure that they could be ticked off accordingly to make sure the procedure was followed and all of the goals and objectives were met on that given day to the timeline. We had the ability to go and map these out, change things accordingly, and actually go, and things were quite fluid, but we also had a set of goals and objectives that had to be met on that given day before we came back in. The underwater navigation system that we were using used a combination of Doppler, infrared and sonar, and then we had a buoy here that actually connected us back in real time to the habitat, which was pretty spectacular. It's hard to get communication or wireless communication like that underwater. I talked about the procedure, so every single thing that we did underwater we used a procedure for. Now, one of the biggest things with astronauts is they get bored easily. So you can't go and send an astronaut into a habitat like this and then send them out on a mission and say, turn over that fake rock. Tell me what that piece of rock looks like and report back. It just doesn't sustain them and it doesn't provide any value. One of the biggest things that we've done in the last couple of years is using coral as an analog for exogeology. So coral is the oxygen mask of the world's oceans. It provides the lifeblood of the oceans. However, one of the issues is over the last 10-20 years, we've had climate change. The world's oceans are getting warmer. So the coral reefs in various places around the world, like the Great Barrier Reef, are dying off because they just can't sustain themselves, and therefore the oceans are effectively dying. If all the coral dies, we're going to have a very serious problem as climate change really begins to take a hold. So one of the things that we've started doing with these missions is coral reef exploration, coral reef identification, working with FIU, working with the Coral Restoration Foundation to identify different genuses of coral that are actually thriving in some adverse conditions, taking those samples, analyzing them, and then possibly doing genetic combination of different types of coral to try and come up with combinations that are more resistant to the change that we're seeing in the world's oceans. And at the same time, using those templates as an analog for exogeology. So how would we approach samples on an extraplanetary surface? What tools do we need? How do we make sure that we don't contaminate those samples? And all of these procedures kind of dial into those same components. One of the best things that we had was a training day where we got to go out down with the scientists from Florida International University, the coral specialists. And he was down beside us and he had his little clipboard. And he went and he'd point to a piece of coral and say, Siderastria. And then he'd go and point to the coral and it's like, okay, that's that, we got it. Move along. Agarcia, okay, yeah, okay. That looks right. Great, fantastic. You have the subject matter expert bringing you down and giving you a guided tour. Fast forward a little bit and you're in a stainless steel helmet 20 meters deeper than you were previously and the coral changes and you can't see it correctly. Then they want you to go and do wordsmithing on Siderastria, Agarcia and Orbicella, and it just became ridiculous. One of the biggest issues that we had is we didn't have enough training. When you were with the expert and he was able to say, well, this is the 3mm polyp, but I actually want you to go after the 5mm polyp. It was almost impossible to see. So this became brain coral, carrot coral, cabbage coral, turnip coral, any other name that we could think of, not to have to say this humongous just list of wordsmithing. So as we went through, you can see that we went and dropped temporary markers on the different pieces of coral. The science team can actually see what we're looking at through the video. We're actually relaying it back to the habitat, to the aquanaut that's in there. But the other thing you have to remember is we're on 30-minute comm delay. They can't see what we're doing in real time. So what we had to do is go and find a different piece of coral that we think represented what the science team was looking for, drop these temporary markers, and then 30 minutes later we would actually go and get the feedback of go and get sample number 2, number 17, and number 21, forget the rest. So this was an interesting component of how do you deal with that time delay. We are not the subject matter experts. The astronauts are not geologists, they're not coral experts. But these are the operators on the ground that are required to go and take these samples. And so this allowed us to go and not only fine-tune that procedure, the tools needed to retain the, I suppose, the sanctity of the sample to make sure that we didn't contaminate it, make sure we didn't contaminate ourselves, the vehicle, and so on, and all of the tools and procedures necessary. But this was relatively interesting and by far one of the most interesting scientific objectives of the mission because it had real world application for what we were actually doing. So how do you go and get a piece of coral out of the coral bed? Well, we had a hammer and chisel that didn't always work, so we had a drill. So you go and give an astronaut that's working in a stainless steel diving helmet, and then you have to tell him that he has to take a big pneumatic drill and drill the sea floor. So needless to say, there was several volunteers who actually used the drill on a daily basis, and this was probably one of the funnest things that we got to do, that you would drill on the sea floor, trying to go and get these samples out of the sea floor. One of the other big risks was if you go and broke off a massive piece of coral, it was like, don't do that. This is bad, we're trying to protect the coral. So we had rescue divers or technical divers that came along that I didn't realize afterwards that had this massive glue gun where we go and actually put the coral back, they re-glue the entire coral piece back on, and then it would actually go and regrow and retake back to where it came off. The pantorometer was what we used to actually go and gauge the health. So this was a series of LEDs that would actually measure the health of the coral before we'd actually go and take a sample to actually get this. One of the most significant things that we actually did as part of this mission was building the world's deepest coral nursery. So you can see these coral trees that we actually built from hand on the seafloor. Each one contains about 200 pieces of coral, and there are 5 coral trees in a row. We had to go, build this component, and photograph every single one of these small coral pieces. This time next year, or 12 months after this mission took place, is we'll go and actually take small snippets of those pieces of coral, and they'll actually be taken and then be replanted on the coral reef. After about 3 years, that tiny little snippet of coral will actually be about 12 feet in diameter. So it actually grows very rapidly. One of the things that we're trying to do here is optimize the procedure and the template for actually regrowing coral and then applying it to different coral reefs around the world. During this mission, so you have all this gear on your back, you're hunched over trying to put these together, and 7.5 hours is a long time. So we actually radioed back, and I tried to get somebody to actually get a hold of Guinness. I was like, if we're building, like bona fide building the world's deepest coral nursery as part of this mission, get somebody from Guinness on the phone to actually go and record this. I was like, this might be the one chance to get into the Guinness Book of World Records with this nonsense. So you can see here, just going and taking the photographs of the little coral samples, one at a time. This was interesting. So as part of this mission, we actually brought down a small handheld manual drilling tool that was actually designed by students. So we brought this down with the idea that we would actually go and test this tool, and the whole concept was you would go and manually drill down into the regolith, and then you would have a small detachable tool that you would actually go, could be taken out, and another one dropped in. One of the biggest issues with trying to take samples and not contaminate them is that the regolith can get caught in the eyelet. The school that actually came up with this particular idea came up with a very unique eyelet that they developed using a modified bicycle tire in the spokes, because the flexibility of that rubber would allow it to actually go and close around the regolith and force something either in or out so it could close completely and then retain the sample without actually contaminating it. One of the most interesting things about this is the spacewalking tools department were so impressed by what these students brought to bear. It's actually going to be refined in conjunction with the students and will fly to either an asteroid, the moon, or a future mission to Mars, which was pretty impressive. We're actually working at the moment and talking to Science Foundation Ireland to try and open up a pathway for both Irish schools, universities, students and researchers to be able to go and propose and enter into competitions like this and actually engage Irish science so much more with NASA on missions like this, so they can actually see their technology, their experiments being used, liaise with the astronauts and actually see them being used and actually try to kickstart and inspire some of the work that's been done. One of the other experiments that we did was testing of optical comms equipment. Testing small LED lights of different colors, different intensities at different distances to see what is the optimal way of actually transferring data underwater wirelessly without contact, which was pretty interesting. So you can just see the setup here that we had on the wet porch that was outside the Aquarius at the time. One of the aquanauts on board was the Naval Postgraduate School expert in ROV, remotely operated vehicle, and then AUV, autonomously underwater vehicles on Aquarius. So he'd been working with us for the last couple of years, and then during the mission he went and guided these small autonomous rovers underwater and inspected some of the equipment, followed the aquanauts, provided additional viewpoints, retrieved some of the samples, brought them back to Aquarius and so on. So this was pretty interesting from that point of view. A couple of missions ago, rather than a journey to Mars, we were working on an asteroid retrieval mission. So we actually brought in these mini one-man submersibles, which were designed to go and mimic one-man spacecraft. So what we do is, we go, the mini spacecraft or submersible would hover just above the seafloor, barely touching down, and then you had aquanauts that were on the end of a boom, effectively, trying to retrieve samples and testing how that would work, what we would need, because unlike a moon or a large body, these asteroids effectively are always slowly turning in space, and to provide the ability to go and land these spacecraft without actually doing damage all at the one time was a significant objective. And then you can see the support divers here tending the umbilicals and so on. So this was kind of cool just to see this in action. Down beside Aquarius we have a full-scale mock-up of a lander that would either go to Moon or possibly onto Mars at a future date. But what happens if we can't actually put astronauts on the floor of another planetary surface, for whatever reason it might be? Well, then using a boom was one of the options that had been proposed. So this was, a lot of testing was done with lowering and upping this boom, actually working on the restraints, looking at how we would actually go and retrieve samples and just do a basic tool setup and traverse from one side to the other. The other thing that we have is we have an underwater climbing wall actually built on the sea floor at a 45-degree angle. So once again, looking at the application of boom technology, the restraints, what's comfortable, what kind of tools will we need, how do we make sure we don't contaminate the sample, retrieve it successfully, and then go and put all of these components together in an operational environment that's just not theoretical, and figure out all of those kinks. This is our change of command ceremony. So Reed Wiseman transferring the Kirby Morgan to Megan. So this is the night before Reed and I effectively came up. So this was just a great photo, a phenomenal crew that we had together. You can see here in the bunks, but facing all the way down into the galley area, and the bulkhead that was actually sealed. So you can see actually the title in the book that we're actually reading. These were contraband that were smuggled down. It's 20,000 Leagues Under the Sea. This actually turned out to be, in 21 missions, the most popular photo in the history of the program. So this went viral actually, and we took a little bit of heat for this, but it managed to raise the profile of everything that we were doing, and we took these home with us, which was pretty cool. One of the best things that we actually got to do was a night dive. So that's myself and Reed outside with Matthias and Megan. So we were outside for about an hour, and one of the funnest things that I got to do in this mission, and one of my best memories, is getting outside, and then we went and turned off the lights. So you're literally standing on the seafloor with nothing around you, and then these green lights from the habitat turn on. And if you remember the scene from the first Alien, where they go and leave the Nostromo and come down and land on the planetary surface, that's literally all I could think of. You have this ship coming down, literally looks like steam, these green lights, and this literally looked like a spacecraft on the surface of another planet. We took about 40 photos that night, and this is the only one that ever came out clear. So Reed's pretty upset that he's the one that didn't get the clear photo as a result, but this was awesome just to see and experience this underwater. talked a little bit about kind of the decompression or the recompression that we did on the O2 protocol. Here's the bunk, and you can see the other bunk above me. That little cubby in the back there is effectively your living space. You had a small area to put all of your personal gear, and then this is the space that we lived in. It was small, but it was cozy. But this was literally the adventure of a lifetime. Ad Astra per Aspera, a rough road leads to the stars. It's a motto that I've lived by. It's the motto of my alma mater as well. But this was the adventure of a lifetime. I got an extraordinary opportunity to do something pretty phenomenal. My crew members, Reed and Megan, would both say that this was the second best operational experience of their lives, surpassed by only going into space. And if that's all that this turns out to be, well then, this was a pretty phenomenal adventure that I got to be a part of. Thank you very much.
Anyone have any questions?
I have a question here. One of the biggest challenges for Mars is the duration of the time. And I was wondering what your views are about robotics versus a man traveling to Mars is one thing, and then the sci-fi aspect, which is very compellingly attractive. We all remember the cryogenics, they waken up and full of life, and they don't have to deal with the trauma of the. Say something.
So I'll take the first one. Robotics are great, and robotic precursor missions, I think, will become more and more of a mainstay of what we're going to do. However, one of the obstacles with robotics is that there's only so much they can do. What Spirit, Opportunity, and Curiosity have managed to accomplish in years worth of work, research, and exploration, we could probably do within a couple of days, if not a week, of a manned crew. The ability to go and put an autonomous being on the surface to make those real-time decisions and calculations of what we need on the exploration components are pretty phenomenal. The other thing is, you ask a question of most people and ask them, do you think we're always going to live on this planet? Do you think we're always going to stay here? And most people would say, well, no, like eventually we're probably going to go and explore somewhere else. And it's like, well, when is that going to start? Do we wait till next week, next year, the next generation, or 100 years from now? My argument would be, no matter how slowly we do it, exploration is ingrained as part of our DNA. And as a species, we have always explored. It hasn't always been successful. But to push the boundaries of what we know, knowing that there's something else out there, I think if we stop, and if we stop exploring, stop pushing forwards, then we stagnate as a species. The other big component is we are overdue for an extinction level event. Like in the timeline of the Earth, in the timeline of the universe, there is some component out there, there is something out there that is going to hit this planet. When that happens, we are going to see a level of devastation that is almost unimaginable. If we have not put the steps in place to actually go and provide an alternative for the continuation of our species, and if we haven't put those steps in place, we may see the end of our species on this planet. So there's a strong case to be made for robotics. I think there's a stronger case to be made for joint robotics and human exploration if the right steps are put in place. The second question in relation to cryogenics. There's actually been a lot of chatter in the last 6 to 9 months of supercooling humans, sinking their core body temperature and the requirements necessary for a deep sleep. They still think that the technology that would be necessary to make that happen is probably at least 10 years off. But it would seem to indicate that current research and steps being taken now, that by the time we get a crew ready to go to Mars, the possibility of 6 months or a longer duration of a super cool sleep might actually become a reality. So from my point of view, that's actually one of the most exciting areas that we're currently working on, and it also has application for conventional medicine and some disease processes that will be able to help and we'll be able to investigate further. So I'm going to keep a close eye on that. I can't wait to see how that aspect actually turns out.
One further question, but maybe someone else couldn't really comprehend on the spaceship regarding on the ISS, the visor 3D Microsoft thing. I recall watching a program on Harland and Wolff and the development of one of the engines for the Airbus, and an engineer proudly displaying behind him a vast data bank of computers and telling us all that there was 600,000 parts, or maybe a million parts, but each one he could go to his laptop and it had a signature and he just type it in and it would tell him everything he would need to know. But there didn't seem to be, in what you said, a similar feature where in an emergency or if you lost something or you needed information about something, there wasn't that fast gathering together centre pool of information.
So, in relation to the supplies for the International Space Station, absolutely not. They haven't done a good job of cataloguing all of these components simply because up until now, really, it's only in the last couple of years, everything has almost been maintenance on board the International Space Station, just getting it to the point where it's a functioning laboratory. The individual components and systems are very well understood and very well maintained. It's the stuff on the inside where we've just been stowing stuff that people have not categorized correctly. Reed Wiseman, my commander when he was on board the space station, one of the funniest things he ever said to me, he would go and spend, one of the most gratuitous things that he could do is he would go and spend his Sunday, he'd get about 6 hours, and he'd go into a compartment and he'd unpack the entire thing. And he'd go and categorize all the 4 layers of these hundreds of items, categorize them, then put them back, and then go and send the list down to mission control. And he actually felt like he'd actually accomplished something. In relation to storage, that would be one aspect that they're trying to get on top of. The HoloLens is still very much almost a prototype technology. Microsoft's pushing it hard, but last year's NEMO mission was the first time that it had been used in any kind of working capacity. Scott Kelly actually flew it on board ISS at the end of his mission, just as a trial run. I think they're trying to compile that type of database for a variety of different functions and actually go and provide that ability using the HoloLens, but it's definitely not there yet. It's literally a crawl, walk, run approach of trying to actually go and manage those systems, because you've got to remember you have components of American engineering, Russian engineering. They're well understood, but I don't think they have that level of what Airbus would have had with the individual parts. And again, you're not in a hangar, you're in the most extreme environment that you could possibly think of trying to go and manage those. I think what we'll see is incorporating that technology possibly for future spacesuits, where you can actually go and actually build that into the visor, and then for next generation vehicles, as we kind of really push the engineering of spaceflight into the 21st century, those components might actually become more available to us.
That would be cool.
And won't it?
The whole WC thing, like this is just maybe one capsule, but is it, I don't know, is there a benefit or is it viable to having like bigger and bigger structures under the sea and having people living there for long periods?
So,
Bioshock's a bad example, but like, is there actually a positive argument?
There's a positive argument depending on what your objectives are. So what we use here is for training, adaptability, getting ready for spaceflight. I would love to see bigger habitats. One of the big issues that we have at the moment for Aquarius is maintenance. NOAA used to own it. They sold it for a minimal amount of money to Florida International University because it was actually taken out of the budget. They were actually going to go and scupper Aquarius on the seafloor, flood it, and just leave it to the fishes. So, would it be cool? Absolutely. The problem is who's going to pay for it. One of the big reasons that Aquarius is at the depth that it is at 20 meters is that most people don't realize that oxygen is actually toxic to the human body at pressure. So if you go too deep on too much oxygen, you actually get toxicity of the central nervous system. It can cause seizures. A little bit shallower, but a longer period of time, you can get pulmonary toxicity where you develop a dry, racking cough within the lungs that can then eventually begin to cause bloody, frothy sputum and actually get fluid in the lungs. The depth to actually cause that pulmonary toxicity of increased oxygen in the system is actually at about 55 feet. That's one of the reasons that the living depth of Aquarius is actually 45 feet. So we can actually live at that 45 feet level indefinitely without the toxic effects of oxygen built in. So Aquarius is actually staged on the sea floor in a sandy kind of basin surrounded by coral, but on a very, very stable platform at a specific depth to make sure that all of the toxic and dangerous effects that we would see from living under pressure and underwater won't be experienced. To have a long-term or much larger habitat, it would either need to be maintained at the same pressure as the surface or built in a similar type of environment to make sure that kind of human beings don't suffer similar type of toxic effects over a much longer period of time.
Just a question, I suppose, about the difference between an underwater sort of simulated spacewalk and an actual spacewalk. Have you had feedback from, say, people who've done both missions, and how they describe the main differences?
So, one of the biggest things, and it's more akin to spacewalks we're doing at the moment, and I'll come back to Nemo in a second. In the neutral buoyancy lab, you saw Paolo Naspali being trained in the big white suit underwater. So they keep that as close to simulation and training quality for actual spacewalks as they can for outside the International Space Station. And they go and they'll train. So for every hour that they do on a spacewalk outside, they spend somewhere between 6 to 10 hours, depending on the mission, in the pool at the MBL. And the whole idea is that they'll go in the same way. They go out the airlock the same way. Hands go in the same way. The astronauts would say that the level of training that provides in specific tasks is very much akin to what they do, because they have the same tools with the same bag and so on.
So it's more about protocol than...
Oh yeah, protocol, procedure. One of the biggest things that they would say, however, and one of the big differences, when you're underwater in the pool, the astronauts will go and they're toggled with 2 different tethers onto the outside of the space station. They'll go and they'll push off, and then the tether gets them and they're over this handhold and they're getting their tools. And Reed said the second time that he was in the pool, the trainer that was with him afterwards told him, "You won't do that in space." And he's like, "Listen, I'm tethered in, I'll be looking around, I'll be looking at the view." And Reed said going out of the airlock, the very first time that he did a spacewalk, you crawl outside and there's nothing but down. And he says, you're hanging on the outside of this ship that's going 26,000 kilometers per hour, looking down at the earth, and he says, you're dead right. You go and you hang on for dear life, because the last thing you're going to do is push off and risk any kind of maneuver. He says it's just the feeling of height is overwhelming once you're hanging around on the outside. And he said once you go and open that airlock, he says just that sense of depth and height, because the airlock goes and you're facing down and it flips open, and he said that was the most significant aspect. He says it's amazing. The view is incredible, especially what Kate Nibbons did on this last spacewalk. She actually installed the commercial docking module on the very, very, very front of the space station. So the space station is huge with these massive arms and all the